Okay, we should be live now. But we still wait 2 minutes until we actually start. Hey. Yeah, we're live on YouTube. Oh. Alyosha just came by.
Right now in Zoom session.
Sorry?
Now we are in Zoom session, send the link.
Okay, I sent you the link, but we will start in 1 minute.
Yeah, but
I already sent you the link.
Yeah, okay, then I have it.
Okay, I guess it's about time to start. So welcome everybody to the 5th BMTT MOTChallenge workshop. So first a welcome from the organizers. My name is Paul, and Bastian Leibel is also in the Zoom call, and also Jonathan.
Yes, so welcome everybody to this workshop. From the look of it, it looks like we have more participants here than at CVPR, at least for most of the papers. And we hope that there will be more participants tuning in as the workshop progresses.
Exactly. Okay, so I had the first session was supposed to be an introduction where the dataset is explained. And I already pre-recorded this and also uploaded this to the CVPR workshop system. And since I already pre-recorded this, I will now just play the video as a screen share. So I hope that the quality will be good enough also on YouTube. But let's just have a try.
Paul, before you start, could you give a quick overview over the outline, the program?
Sure. Okay, let's get this over here. So we will start with intro and welcome, where we are just in. Then there will be 2 invited talks, first from Bernd Schiele, then from Raquel Otterson. And Raquel will not be live here today, but we will play a video of her. Then we will announce the results of challenges 1 and 2. Afterwards, the winners of these challenges will present their methods in an oral presentation. Then we'll have an interactive session with some discussions, hopefully good discussions here on Zoom. Another invited talk by Shen Wang, who on short notice stepped in because the actual planned talk was cancelled. Afterwards, we will have challenge 3 results and the oral by the winner. Then we'll have some spotlights of other participants who didn't make the first place. Another discussion slot, then another invited speak by Alyosha Efros, and wrap up and closing. This is the program for today.
So here for everybody, we're still new to this format of online workshops, on online events in total. For this schedule, you can also find it on the workshop webpage. The important fixed points will be the times of the invited talks. So if at any point you need to leave during the workshop, be sure to tune in again and you will always be able to catch up at those invited talks. In between, we will have to see a bit how long each of the session takes. We have guidelines for the timing, but also we hope for very interesting discussions, but we will always start the invited talks on time.
Okay, thanks, Bastian. So I'm now gonna play the introduction video, which will introduce a bit the data sets and the challenges. So as I said, I already pre-recorded this before. The sound should now also be shared, so let's have a try. If this for some reason does not work well, just let me know. Hi, I'm Paul, and I'm going to introduce you to the 5th BMTT MOTChallenge workshop on multi-object tracking and segmentation, or in short, MOTS. So today I'm going to talk first about the motivation for this workshop. Afterwards I'm going to introduce the datasets used for the challenges and the annotation procedure we use to annotate these datasets. Then I'm going to introduce the evaluation measures used for the challenges, and in the end I'm going to briefly introduce the 3 challenges used for this workshop. So let's start with the motivation. So by now there are many datasets available for multi-object tracking. However, these are usually only annotated on the bounding box level, while in this workshop we want to look at tracking at the pixel level, so we cannot directly use these datasets. Also, when you look at these images, you will see that in these difficult situations, bounding boxes are a very coarse approximation to the objects. For example, if you look at the dark blue car on the bottom images, you will see that most pixels under the bounding box of this car do not belong to this car but to the red car instead. So in this case, the bounding box is a very poor approximation to the object, and the segmentation mask carries much more fine-grained information. And this segmentation mask information could be used to train methods to achieve higher accuracy. And also, if we have a method which outputs segmentation mask as a result, this could be used for further applications which get the tracking result as input in order for them to use much more fine-grained information. So let's look at the datasets we used for this workshop and how we annotated them. So first of all, we have to note that creating dense pixel-wise annotations for every object in every frame of the video is super expensive. So in order to solve this, we used a semi-automatic annotation procedure which we introduced in our CVPR paper in 2019. Using this annotation procedure, we annotated for this workshop both the Kitty MOTS dataset and the MOTChallenge dataset, both of which we will look a bit more at later. So let's first look at how the semi-automatic annotation procedure works. So first of all, note that we do not start from scratch, but instead we use existing bounding box level tracking annotations for the dataset. When we have these, we take a fully convolutional network which we call box-to-seg, which gets a crop of an object as input plus the bounding box encoded as a force channel, and then it outputs a segmentation mask fully automatically. However, of course, if we do this like this, there will still be some errors in the results. That's why we'll need some manual corrections. For this we have the following diagram which outlines the semi-automatic annotation procedure. So first of all, we take the box-to-seg network and train it on some other datasets which are already annotated, like Mapillary and Coco. Once we have done this, we go track by track. And in the first iteration we do not have any manual annotations yet, so we just take the bounding boxes, evaluate box-to-seg and generate segmentation mask automatically. However, this will contain some errors. So we have a quality assurance step, which means that we have annotators which look into the results and find erroneous masks. These are then manually annotated with polygons. After we have enough newly collected polygons, we will retrain box-to-seg using all the polygons of the target dataset we want to annotate. After this global retraining, we will again look at every track, and for each track we will also have some polygons now. So for this particular track we will fine-tune on the polygons we have obtained for this track, and after the fine-tuning is done we will evaluate box-to-seg on this particular track to get better segmentation masks. Again, we will have a quality assurance step to check the quality. Maybe we need to pick some more erroneous masks and correct them and iterate a few times. But at the end, we will reach our quality standard and the dataset will be annotated. So we use manual corrections here to ensure a consistent and high quality and make sure that there are no remaining errors in the dataset. This also yielded very large savings in time. So for instance, in kitty MOTS, only 13% of the car bounding boxes had to be annotated manually. And for MOTChallenge, only 15% of the pedestrian boxes. So let's now look at the actual datasets. So the first dataset is a kitty MOTS dataset, which is based on the kitty tracking dataset by Geiger et al. 2012. So let's look at a short video which demonstrates this dataset. Note that there are gray areas which are usually far away, which are ignore regions as defined by the original kitty dataset, and all the cars and pedestrians will be annotated on a pixel level. So in total, for training and validation, we have 21 sequences and 8008 frames, 167 tracks for pedestrians and 581 tracks for cars. Then we also have the test split used for the challenge, which has 28 sequences and 11,000 frames. So we have a second dataset called the MOTChallenge dataset, or also MOTS 20, which is based on the original MOTS 17 dataset, which was annotated on a bounding box level. And here we added the segmentation masks as well. Here we only used 4 sequences for the training set and 4 for the test set. Each split has roughly 3,000 frames, and the training set has 228 pedestrian tracks and 328 pedestrian tracks in the test set. Also here we can look at a short video to get some feeling for the dataset. So it's very crowded scenes, very challenging. Okay, next I'm going to talk about the evaluation measures used to determine the winner of the challenges. So first of all, we consider the clear mode metrics, which are well established for multi-object tracking, and here we consider mask-based variants of them. So for the clear mode metrics, you first need to establish a correspondence between the hypothesized objects and the ground truth objects. For box-based tracking, this is non-trivial because the boxes can have overlap. So usually a Hungarian matching procedure is required to establish the mapping. However, in the mask-based case, which we consider, we require that all masks have to be disjoint. And this makes the correspondences unique and straightforward to determine. So a hypothesized and ground truth mask are matched if and only if their mask intersection over union is larger than 0.5. Once we have the correspondences determined, we can define the MOTSA, MOTSA, multi-object tracking and segmentation accuracy, which is closely related to the MOTA evaluation measure. So this is derived using the true positives, the false positives, ID switches, and we normalize by the number of total ground truth segmentation masks. Then we can also define the number of soft true positives. So here we do not just count how many matches with at least 0.5 overlap are there, but instead we go over all these matches and accumulate the actual intersection over union. And when we normalize by the number of true positives, we get the MOTS P, multi-object tracking and segmentation precision. Then we also finally define the SMOTSA, soft multi-object tracking and segmentation accuracy measure, which replaces the number of true positives by the soft number of true positives. So it combines tracking and segmentation quality into a single measure, and this will be the evaluation criterion used to determine the winner of the challenges. So let's look at the 3 challenges. So the first challenge is on the MOTS 20 dataset for pedestrian tracking. The second one will be on the kitty MOTS dataset for car and pedestrian tracking. And the third challenge is a tracking-only challenge on both datasets together. On all 3 challenges, the methods will be ranked by the SMOTSA evaluation measure. So let's look in detail. Challenge 1 on MOTS 20. Here the task is multi-object tracking and segmentation, or in short MOTS, of pedestrians on the MOTS 20 test set, which in total has 4 sequences. Here no detections or segmentation masks are given, and the methods must perform all parts of the task, so detection, segmentation and tracking together. Also the same method with the same parameters must be run on all 4 sequences, and we do not allow sequence-specific tuning. Challenge 2 is multi-object tracking and segmentation of cars and pedestrians on the Kitty mod test set of 28 sequences. Again, no detections or segmentation masks are given, and methods must perform detection, segmentation and tracking together. Here the hyperparameters and the method can be different between cars and pedestrians, but for the same class, the same parameters must be used for each video to encourage generalizable methods. Here we also allow methods to use stereo, LiDAR and GPS data if they wish. And the ranking will be determined by 50% the MOTS score for cars and 50% the MOTS score for pedestrians. Finally, challenge 3 is a tracking-only challenge. So here detections with masks are already given to the participants and these must be used. So the methods must only sub-select from these masks and assign these masks to track IDs. In order to have a reasonable setup, we started with a strong detector, mask RCN X152 of Detectron 2, to generate very strong detections, and afterwards we ran box to seg to improve the segmentation mask quality. So this tracking-only challenge will be evaluated on both the MOTS 20 test set for pedestrians and the Kitty MOTS test set for cars and pedestrians. Here methods are strictly not allowed to run any additional detectors, but instead the given detections must be used. Methods here are also not allowed to use stereo, LiDAR or GPS on the Kitty dataset, but only monocular images. The ranking will be determined by 25% the MOTS score on Kitty for cars, 25% the MOTS score on Kitty for pedestrians, plus 50% the MOTS score of pedestrians on MOTS 20. Okay, so this was the introductory video. I hope that audio and video quality was okay. So next on the program will be Bernd Schieler with his invited talk. And I think Bastian wanted to give the introduction here.
Mm-hmm. Yes.
Should I already start sharing screen?
Hi, Bernd.
Hey. Can I already share screen actually start, I guess? Can you see my screen?
Yes, we see your screen.
Yes, very good.
Perfect, good.
Okay, we have a couple minutes
Sure.
before we need to start. So here an opportunity for everybody. Of course, workshops live by the participation of all participants. So in case you have any questions, we will hopefully have a few minutes after the talk to answer those questions, hand them to the speaker. You can already ask questions by chat. And if later on, if you want to ask questions by voice, please use the raise your hand feature in Zoom. So when you click on participants, there is a symbol for raise your hand. When you do that, this will appear as a signal for us, and then we know that we can assign the speaking right to whoever is next. So I think we can already start with an introduction of our speakers. So we are very happy to be able to now proceed with the first talk. This will be given by Bernd Schieler. Bernd did his studies on computer science in Karlsruhe and Grenoble, and then got his master in Karlsruhe, his PhD in Grenoble. That was back in 1997. He was then a postdoc at MIT from 1997 to 2000. And starting in 1999, he moved to ETH Zurich as an assistant professor, and he stayed there until 2004, at which point he got a full professorship at TU Darmstadt in Germany. So he stayed at TU Darmstadt until 2010. And in 2010, he was appointed director of the Max Planck Institute for Informatics in Saarbrücken, where he is currently leading a very big lab and continuing to make amazing contributions to computer vision. Bernd's research has been very influential in computer vision, with important contributions in pedestrian detection, tracking, and many other areas. He has an age index well over 100, and many of his PhD students and postdocs have gone on to become faculty members of their own. So one can safely say that he has had a huge influence on the way how this entire field has developed and has been shaped in the last decades. So we are very happy and honored to have Bernd as our opening speaker for our workshop. And we are very curious about the content of your talk.
Yeah, great. Thank you very much, Bastian, for the kind introduction. So what I wanted to talk about is not directly at the core topic of that workshop, and it's actually amazing and very nice that you have this very nice data sets assemble and organize these challenges. We have been working on segmentation and tracking for a while, and we have used some of the data sets, but not the segmentation part yet, but we'll definitely look into this in the future. What I wanted to talk about is a problem that we all care about, though, which is sort of the robustness and security of computer vision and machine learning in particular. And let me just briefly mention what I mean by that. So when we all now use, obviously, machine learning in all kinds of ways, right? So we are always starting with some data, right, that we are training our favorite machine learning model, typically a deep learning model these days, right? And then we are deploying it in the world, right? For example, for segmentation, semantic segmentation, for tracking, whatever. And the thing is that these the machine learning models obviously have all kinds of what they call attack surfaces, right? So the one thing that everybody knows is sort of if you have some adversarial perturbations, right, and you add them to the image, right, you can get all kinds of outputs at the end eventually, which are really sort of completely off what the model was intended to do. So it's really adversarially attacking the model to do something completely different than it was intended to. Another thing is actually that if you deploy your machine learning model, and for example, as an API, and I will talk about this later, then you're having your machine learning model and somebody just starting to basically steal your machine learning model, despite the fact you want to protect it. Obviously, you want typically to make some money or sort of want to sell the functionality in one way or another to amortize your own investment. So there is really this kind of two questions I'm going to talk about. There's another question I'm not going to talk about here is what's called membership inference. That actually is sort of a privacy problem. If you're starting to sort of infer from the machine learning model output, you're starting to infer actually what kind of data was used. And then you really can start reconstructing, for example, faces, images, right, really of people, of scenes that you have been using, and really literally stealing the function, the inherent sort of data that you had collected. And we all know data is as one of the key assets these days. And obviously, if we have something that is more trustworthy at the end of the day, we're really having encapsulated this, the data as well as the model itself, and actually it is less attackable with the real attacks like adversarial attacks, and it's more robust, more secure. So that's really sort of the whole game here in a way, right? And it's one of those things with obviously a moving target. It's not so clear what exactly we have to do to really get it right. And then at the end of the day, it's also a bit of a race, obviously, from the attacker versus people who are developing the models. But I think this is a topic we really need to far more look into this than we currently do. Let me talk about three aspects here, depending on time, but I'm planning to talk about three aspects. The first one actually is one, the bright and dark side of scene context. That's based on two papers that I'm going to briefly talk about. It's an enourage paper and 2019 CVPR paper. And let me start by pointing out the problem. So the problem here is the following. So take this image here, right? And if we use sort of a reasonably up-to-date sort of state-of-the-art image segmentation method, like the UpperNet, right? It will basically tell us here are the cars, here are the road, here are the sidewalks, here are the people, and so forth. We'll do a pretty good job in terms of really labeling the individual pixels to the semantic class that we are interested in. So now what we did here, actually, we removed the cursor on the left side of that image, right? And what comes out actually is that on the right side of that image, all of a sudden, the sidewalk is not correctly classified anymore as sidewalk. And it sounds actually surprising a bit, right? Because it's really far away as a scene in the scene, but somehow actually it is quite understandable. If there are cars parked on the left side of the road, it's kind of more likely that there is a sidewalk on the right, right? In that sense, that actually it's a good thing to use the context when it's there, but when the context basically is misleading or different than what you have seen in the data set that you trained on, it's starting actually, the model starting to basically not work correctly anymore. And we see many, many cases of this, right? Where it's good to use context, but if it's relying too much on context, we have a real issue. And that actually is the topic here, basically, of this first part of the talk. Okay, so what we're looking at is in a particular aspect that is of objects, so co-occurring objects. And we want to do two things. The one thing is we want to quantify the context sensitivity, right? And that really was the topic of the NeurIPS paper, by removing objects and see how it basically behaves when we remove objects, how other object classes are affected. And then we want to also use this method basically to augment with sort of scene contexts that have not been seen before, that are really not working well, to hopefully achieve better performance. I will not talk a lot about the exact way we're doing this object removal. There's an entire NeurIPS paper about this. I just want to make the point that we're basically, the input here is an image and a label. Here we're just saying, remove me the dog. We don't give the bounding box. We just say, well, remove me the dog in the image. And what comes out is roughly this, right? If you use the mask-based CNN, basically you would get roughly this. So what our algorithm does is slightly better. And also here, we're removing the person, right? Just by telling, remove me the person. Here, we remove the airplane and so forth. So we have a method basically to remove objects from scenes in a pretty reliable way, resulting in images that are pretty close to what we want. They're not perfect, obviously, but they're pretty close. Okay, so as I said, I want to do two things, right? I want to quantify this, right? And I want to use it for data augmentation to quantify the problem. So what we do basically, we take an original image, right? Then we remove, one object at a time. We have a list of objects in the image, right? Then basically this is, so here in this picture, we remove the mouse. In this picture, we remove the keyboard. In that picture, we remove the monitor. And you basically look what your current model does, right? Your target model that you're, in that case, the object detector or a segmenter, we did both. And then you basically verify how good the results remain if you remove sort of one of the objects, some part of the context, right? And if you basically find some inconsistency that actually the context is too heavily relying on the system, right? You're stating, you're using it for data augmentation, right? So what does it mean to rely too much on context? And let me give you one example to roughly state how we measure this. So here the object that we're looking at is keyboard and the context is the monitor. So both are objects, but the monitors are context for the keyboard. So this is the original image. Here we have monitors and here we have the keyboard. In principle, we are detecting both reasonably well. So now basically here in this image, now we have the object, we still have the keyboard, but we remove the monitors, right? And here you want to still have the keyboard detected, even though there is no monitors anymore, right? And in particular, you want to have the score higher in that case than in the case where you do have the context, in that case, the monitors, but the keyboard is removed, right? Here, there's no keyboard. There should be no score for the keyboard. And what turns out to be pretty often the case is that actually the keyboard detector is really relying on context like the monitors, and the keyboard score here actually is higher for this image than it is for this image because it's too heavily relying on the context, okay? So when we do this data augmentation, that's a violation of the consistency in this object detection case. And though we basically want to data augment images with these kind of settings and then basically retrain and hopefully do better. And then here in that particular case, we get the keyboard scores then higher than in this image where the keyboard really is, then it's in that image where there is no keyboard. So here is basically this kind of picture to show actually where the issues are most prominent, right? It's a COCO data set. Here are violations in the original model, right? The higher the worse, but you want to have it as low as possible. And here violations in the data augmented thing, right? So you really want to move all these guys over here. As it's not so surprising, the one actually that is actually pretty well detected actually is the mouse, right? The mouse that you have next to your keyboard, but actually it's too small really that an object detector really does it well. So here it's really relying heavily on the context. We can do much better when we data documentation. But as you see, sort of with ball, even keyboard, book, bottle, with many objects, we have the issue. It's relying too heavily really on the context. So we really want to move these things over here. Let me show you more examples now for the segmentation case. This previous one was for detection. Now it's for segmentation. So here I have the original image, right? A classic UberNet does the right thing, and our model does as well. Here we basically remove the cars. So here are cars, right, that we removed. So here now the UberNet all of a sudden thinks actually there is a sidewalk, and our data augmented method model does the right thing. It actually detects that there is a segments properly the road here. Here's the image I showed you before, right? The cars here, we remove those cars. The UberNet basically has these issues here with the sidewalks, and our model that is data augmented actually does better here. Two more examples. So here's actually an example that I find pretty striking actually, right? So here, take the original image. Here we remove the trees right here. And while the original model, the UberNet did properly say there is grass, it already says there's earth, right? Because as there are no trees, right, there is more likely to be earth. It's kind of really surprising if you look at this locally. There's no, I mean, to me at least, or for most humans, there is no real evidence that this should be earth, right? And again, our model does better. And here, the last example is actually one that actually tells us a bit about the real issue of this when we really do this for autonomous driving, for example. So here we take this image here and we remove the car here again, right? So we have the car here removed. So in the original image, UberNet does the right thing, but here all of a sudden, right, it does actually wrong, right? So there's still a bit of road, but there's water and earth again, right? So it's really sort of doing pretty badly here. In a way, this is one of those cases where the you don't have many images typically in these data sets that are actually having lots of snow and watery streets, right? So in that sense, the only way basically you can detect basically the street or the road in that case right here at the label is actually by knowing where the cars are. So the car context helps a lot here. And as soon as you remove the car context, all of a sudden, right, the network actually is lost. There's really sort of a tail part of where you have not enough data really to train things. And when you basically explicitly search for those cases by, exchanging the context and then explicitly make augment the data to improve on this, then you can really gain performance with this kind of model. Okay, so yeah, so what's the take-home message for the first part? So clearly we have these good things. We want to have context used in the models, right? But they're too dependent on the current scene context. We have this testing framework. It's essentially this enourage paper where we automatically generate different kinds of context via object removal and then reveals weaknesses, as I already pointed out. And then we can also use, obviously, this new data augmented, these images that we generated to overcome some of these context dependencies. And I guess there's somebody asking a question, right? I'm wondering if UberNet fails due to artifacts induced due to inpainting. Yes, so it's a good question. Obviously, yes, in our example that I show, basically, I have artifacts in the images. That's absolutely correct. We also showed, however, that these problems that we are identifying are essentially also transferring to other data sets, like where there's no artifacts. Basically, there's these out of context images. I mean, in the paper, we have several data sets, and when we data augment our system, we also do better on this out of context setting. So it's not just the artifacts; it's really also because the context really is an issue. So we can basically reproduce this after we found these issues. But yes, that's a clear and obvious question, and we obviously verified this in the paper. And clearly, in my view, there is much more work required here in this direction. Okay, so let me move on to the second topic, which is about adversarial robustness and generalization. That's a CVPR paper from last year. Let's joint work with David and Matthias. And I guess all of you know what adversarial examples are, right? So take your, classic image here. This is amnesty in that case, right? Add some perturbation that's typically sort of really adversarial perturbations, and that's sort of enhanced here that the blue and red, right, is adding and just subtracting some pixel values here. And then you see it's actually probably not very visible on the screen, but here this upper left one, which is clearly 0, gets actually classified as a 9 here. And there's this open question in the community, in a sense, right? That accuracy, the hypothesis that when you want to have high accurate model, right, then you can't be very robust. And if you're very robust, you can't be very accurate. And in a sense, there is this plot here that has been shown in one paper here, this archive paper, where there seems to be sort of a front. You want to be basically very accurate, right? And sort of at 100% here, and at the same time want to have a very high robustness. And the robustness here is actually measured as, you know, what sort of distortion you need, what's the distortion you need to get actually wrong result. You always can get the wrong result by distorting it enough. You want to be up here. And it seems there is a front here that you can't be sort of, you know, robust and accurate at the same time. So when we started working on this, it turned out to us actually there is different things that actually we have to distinguish here. And let's see a mock-up example just to make the point. So here, let's assume this is the class manifold of the 5, just some surface, just some circle here, basically in hyperspace, and the class manifold of 6 or some other classes over here. This is the true bounding, the decision boundary. Then we have sort of the classifier's decision boundary. So it's obviously a bit off, but it's not totally off. So the first thing that we found, and that I'll show an experiment for this, that the so-called regular adversarial examples, the classic adversarial examples that, you know, pretty much everyone tries to find, they actually kind of start leaving the manifold. In MNIST, that's actually pretty simple to see, right? Because the MNIST are really sort of binarized images, right? And then if you see actually the adversarial examples for MNIST, what happens is that they're really sort of noisy pixels in the background and as well as on the foreground. So it really clearly sort of, these are never part of the training data, right? They're really leaving the data you ever see, right? Training. So it's really they're leaving the data manifold that you have. Right, so there is then the question, obviously, are there also on-manifold adversarial examples? So if you really have sort of a manifold, right, the real class manifold, can I also find, with a classifier that's well-trained, can I also find adversarial examples that are really proper examples of a 5 here in that case, right, but still confuse my classifier? And it turned out I always can't find those. This is actually pretty devastating in a way, right? Even if you have millions of training examples, we did this experiment. If you have millions of training examples and you're searching for adversarial examples within the data manifold, you still find them. Our networks are simply not good enough and robust enough. There's some, you know, there's some Swiss cheese hypotheses that there's always holes that basically confuse your classifier. But unfortunately, it's really the case. We can always find these on manifold examples. They're harder to find. They're not as, you know, you need more iterations, you need more effort to do this, but you can find them. There's one that I just want to make the point once here. There's something we call invalid adversarial examples. You have to be very careful when you read these adversarial example papers. Some basically generate adversarial examples that are basically, if you change an image from a 5 to a 6 by just, you know, changing enough pixels, it's a 6, right? It's not anymore an adversarial example. It is a 6 that you should classify as a 6, right? So this is not what we call an adversarial example, and some people confuse this in the literature. So somehow this is actually something that we got quite confused about at the beginning until we realized this just you know, really people make a wrong claim here in our view. So how did we do this test now for on-manifold versus off-manifold? And for this, we basically started off actually with a data set where we had access to the latent space. So we had sort of the character dimension, we had a font dimension, and then we basically had affine transformation. So we had a complete description of our latent space, if you like. And then we had a deterministic decoder that actually generated images for us, right? So from that latent space. So which means if as long as I have basically a valid sort of a latent code here, I always can generate a correct on-manifold image here for those cases, for those font images. And just to make the point, classically, right, when we look at sort of the adversarial example setting, is we are basically you're having this axis, the input image, and you're adding some delta such that you basically get the maximum loss here, right? While the delta should be in some epsilon ball, in some norm, some p norm, right? But you're basically trying to do adding this noise directly in the image space, right? In our case, what we're doing, because we have this decoder, we're adding this noise here in our latent space, right? So we're adding that in the latent space, which means we're always on manifold when we do this, when we do this attack, this adversarial attack. So here it's sort of shown here with the original encoding, right? Then I basically add a bit of noise, adversarial noise in the latent space, and I'm getting by construction an on manifold example right here from that image. And then we do still the classifiers before for misleading the classifier. Okay. And here is sort of an example to show what the differences are. So here, let's start with the fully simulated things where we have the fonts. We know the true manifold, right? So here, that's sort of the classic adversarial examples here. Basically, the adversarial noise. You see, you're adding pixel noise in the background where there shouldn't be anything, but then the unmanifold attack basically deforms and affinely deforms actually the letter, right? So basically moves it, scales it a bit and whatnot, right? So it does somehow, I mean, it's bit by construction, because the only way you can actually get the wrong classification is by an affine transformation, but still it does actually that's exactly what we want. So now we can actually also learn the manifold, because obviously if I had the manifold, I would be done with my classification problem in the first place. So I can't assume this in practice. So what we did here, we had sort of a variational autoencoder trained that manifold, and now we're still getting very, very similar patterns here. But even if I do this on sort of EMness, right, it's very similar. And even, right, if you look actually here, now we're doing this on fashion MNess, right, it's a slightly more complex data set. If you go here from back, right, to something else with a classic adversarial noise, again, you're seeing this, scattered all over the place. And here, basically, again, this on-manifold attack with this learned manifold, we're seeing actually, again, we are starting to slightly deform this back, with some affine transformation, essentially, right, to misclassify. So it really seems to do sort of the proper thing, that you really sort of slightly deform it, and then our classifier is still lost. Okay, so here's some statistics just to make the point that we're really leaving the manifold here in this case. So here, if the manifold is known, right, obviously if I have an on-manifold attack, right, the distance is 0. But then if the regular adversarial examples are having a distance that's larger than 0, right, that's what we see, and actually all of them, right, none of them basically stays on the manifold. And if I have a manifold that is learned here with the variational autoencoder, as I said earlier, right, so here the on-manifold examples, right, because they're not perfect, obviously, but still they are basically close. I have a smaller distance than the ones that are classically found, right? And we have a factor of 2 or something, a distance, right, from the manifold. It really is these regular adversarial examples leave the manifold. It's actually quite intuitive if you think about it, right? Because it's the easiest actually to do an image that then a classifier has never seen before. So then basically leaving the manifold is the easiest space to go. Okay, so now back to my original question, right? So how is it actually really true that robustness and generalization are contradicting, right? So that there's a trade-off between the two. It turns out actually in principle, this is not the case. So let me show an example of an experiment exactly for this. So here we're measuring the adversarial robustness by off-manifold success rate, right? The lower success rate the more robust it is. You're saying within a certain epsilon or in a certain number of iterations, some fixed setting, you're allowed to find something, and the least and the less successful, the more robust this is, right? So if I do this regular adversarial training, maybe I should just say what this is. Classic adversarial training is you're having sort of your real images, and then you're during your training, you also have always adversarial samples that you generate while you train, and you add them to the training set, and that actually does increase robustness, right? That's sort of the best known method of achieving higher adversarial robustness. If I do normal training, right, and here actually as a function of the more images I have, I'm improving this robustness. If I do normal training, I'm basically not doing this. So here, more training data really leads to better robustness. That's the point of that plot. So now is the question, what's the trade-off? Is there really a trade-off between robustness and accuracy? And it turns out there is not actually. So here, this curve basically is now as a function of test error. So I want to be on the left, right, the lowest test error possible, and at the same time as low as possible here with the robustness. So using that same curve, but plotted now differently. So as I have more and more data, I get better and better in test accuracy, but also getting better in robustness to adversarial attacks. So that actually is really contradicting what actually is the common belief out there in principle. So why is then there this common belief that there is this trade-off here? And the reason for this actually is essentially there is sort of the sample efficiency problem. So here, basically now let's plot actually the test error as a function of the number of training images. So now in the normal training, right, this is quite a bit below, which is better, right? It's more sample efficient, right? With let's say with, I don't know, here was 20,000 samples, for example, I get sort of a test error around here, right? With the same number of training images, and then sort of doing adversarial training, right? So basically using this 20,000 image plus another 20,000 adversarial samples, right, in each iteration, I can't reach the same test error eventually. So there is, for a fixed training data, I'm still having this trade-off, unfortunately. But it's not really, it's not inherent in the models. It's more a problem that the networks have to train more and more difficult problem, and so they're not as sample efficient anymore. So maybe if we increase the sample efficiency for training, we could actually, get rid of this trade-off we mentioned. Okay, so right, so here, in my view, really, adversarial robustness is not that well understood. There is quite a lot of papers out there. If you go to arXiv, it's one of the the keywords that actually is having lots of papers. I really think it's very essential to make this distinction between the regular, the on-manifold, and the invalid adversarial examples. As I pointed out at the beginning, it's very active, but not all work is great. It's really, be very careful to check what people do. As I said, the regular adversarial examples leave the manifold. That's kind of quite intuitive when you start thinking about it. It's really, that's the easiest place to go in order to fool your classifier. And the regular robustness and generalization are not contradicting a priori, right? So we could actually hope for architectures or the right way of training that we really could get both generalization or high accuracy and high robustness. And as I said, sort of these on-manifold adversarial examples are actually, they exist. As I also said, they're harder to find. You need more iterations. It's harder to, from an implementation perspective, it's more tricky, but they do exist. And actually, I haven't shown the statistics, but as I mentioned earlier, right, even if you train on many data, right, and again in our fonts data that we can simulate, you can train literally on a lot of data. Still, even though you train on millions of samples, you still find on manifold examples. And that actually is a bit, how to say, at least for me, it's devastating. We're not having methods that really are robust even for good for on manifold attacks. And I think because given the time, I think I'm stopping here and I skip and I leave a bit of time for questions. Thanks very much.
So thank you very much, Bernd. Yeah, that was very interesting insights. Are there questions from the audience?
From the 5 people in the audience. Oh no, there are more by now. Okay, cool.
Yeah, thanks, Bernd. There was one question in the chat from Leonid. So the question was.
I answered this question on the go, right? That was actually, yes, I said, right, so you have the UberNet, obviously, about the artifacts, right? So, and I responded to this, I can repeat this. So the artifacts obviously influence the UberNet, right? But we also have results on basically artifact images where we could reproduce the same things on other data sets, right? So once we had found sort of those statistics, we could actually reproduce these problems on other data sets. So the problems are the same essentially, right? We just use those generation to find them explicitly and targeted.
Mm-hmm. So here, one question about those on-manifold adversarial examples, because those seem to be the really tricky cases. The way how adversarial examples work is you push in some direction and your classification boundary is crossed. But that means that the networks don't seem to manage to really get convex regions for the true classes.
So right. So yes. So there is actually a whole how to say, it's not so clear actually how the decision boundaries really look like in our network. So I drew this picture here, or we have this picture here, which seems like to suggest there is some convex region, right? So, however, it seems literally there are really holes. It's more. It seems it's a very. I mean, yes, there is some compact region that might be well classified, but there is also pretty much everywhere there are holes, right? So these on-manifold guys are not. How to say, they're not basically at the border or in the regions. I mean, they're also at the border and they're also in low density regions, but they also in the very high density regions. So it's actually, it's our imagination of this space, because it's so large, or our function space is so large, it's really, it doesn't fit, right? It's not just a convex hull. That's also what we always thought, but you can literally, you find in high density regions, you also find on-manifold adversarial examples, and that actually is not with less probability or something. So it's really sort of not so clear how those classifier spaces are. The problem is that you might just find a little hole somewhere, right? I mean, some have hypothesized actually literally sort of some Swiss cheese thingy. So if you find an adversarial example, another adversarial example, you can find even an entire sort of line in between them, right? In the same, I mean, not a straight line, but a slightly bent line that they can interpolate. But it's pretty, I mean, it's pretty amazing how sparse that space is that we're classifying, it seems. I mean, I don't have a final answer here, but it's less intuitive than we would hope. That's the one thing I can say at this point.
Okay, yeah, thank you.
Sure.
There was one more question in chat.
Yes. Oh, the object removal in the first place. So yeah, so the why we did the object removal. So the whole idea in the first work was that we wanted to test these problems, right? So, but that about the context, right? If you remove, again, let's take a let me see. So, right, let me just take this example here, right? So if I remove those cars here, right? So then I basically can see actually how it goes wrong. That really the motivation of us was initially really understanding the robustness of our models. And here we really discovered that actually it is not robust at all. So the whole idea was really that, right? So we wanted to have testing cases. We have actually a follow-up paper that actually does this even more sort of continuously, right? We're really sort of removing objects and exchanging objects. But the whole point is we really want to understand sort of robustness problems here. Right. So then there's the question: are we also working to fix it? Yes, and that's exactly what I said, right? So the second part of that thing, right? We are doing this here. We're finding the problems, right? And then we're using the data augmentation. We're using the data that we found actually has problems, and we use this to data augment. So in that sense, we can actually improve a bit. And again, in the paper, we have results where we really show that we can, improve results on out-of-context problem data sets that explicitly were designed to show problems with context, right? Great. Oh, but that's okay. Okay, good. So let's have, I guess. Did you try to introduce new context to confuse the models? Did we do that? Right. So actually, no. So right now we are sampling from the well, okay. So yeah, no. Actually, well, yes and no. So we cannot do basically generate all kinds of context. The kind of context we can generate right now is basically by removing objects, which means you're limited in the kind of context you can generate. You can't generate all context, right? So if you wanted, let's say, to have the car in all kinds of situations, like on the grass or in the forest, all these things we can't do at the moment because we only do it based on object removal. That is a limitation. And that's why I'm saying that we really need much more work in that direction. But as I said, what we're doing right now is actually we're changing, that's a paper under submission, we're having a system where we basically we're manipulating the image in a way that actually is becoming really, it's going out of the space of potential images that are in the data sets. We basically trying to generate more and more images by a continuous optimization to cross the border. Like in adversarial examples, you always try to find sort of an addition to the image or a change to the image that really gives you a better sort of a changing classifier. In our case, we really want to have that on the data manifold by basically changing the objects such that they're really looking still like the objects. Like the car, we're changing the car, the color, right, the orientation, its shape a bit slightly, but still such that actually really looks for humans like the objects. Okay, I have one more, I guess. So that's YC asking. Oh, right. Oh, you're asking about the fixing problem. Okay, so there was this question if it's great to identify a problem, but also if I'm working also to fix this. And that was actually the question about the adversarial examples. Yeah. So right. So here for the how to say. We on the second part we haven't really found yet a way to fix it. That's true, but actually so my problem right now is it seems that we're not really understanding the problem well enough, right? This on manifold adversarial examples is in a way sort of more novel still, right? And as I said, so that the characteristics where those are seems to be how to say not that easy to work on. To be fair, the way actually I think we need to address this is by actually going a lot of steps back, right? So right now, the key problem in my view is from our deep networks is the classic machine learning assumption that small input variations actually cause small output variations is violated. So I think we have to work literally on different architectures, different ways of propagating our input-output settings. And that's actually that I think we need to get more robust networks before we really can address this problem of adversarial and also the on adversarial on manifold adversarial problems. So I think we need better architectures. That's something we're actively working on right now to actually have better, more robust architectures that hopefully don't have that problem really anymore, or at least less. Okay.
Yeah, thank you very much. Thank you very much. I think this was a very nice closing word. It's been amazing to see the progress in architectures over the last years, but it shows that there is really still potential for further improvements.
Okay, cool. Yeah, thank you very much for the invitation. Yeah, thank you.
Yes, thanks, Bernd. On YouTube, there was just one question, if you can share the slides. So is this okay for you? It would be great if you can send them to me, then we'll put them on the website.
Yeah, I'll send it to you, right? And then you can put it on the website. Sure.
Yes, that would be great. And there was one more question on YouTube. I'm just not quite sure if we still have time for this now.
Yeah, I think in the interest of keeping the workshop schedule, we need to move on to the next talk. But again, thank you very much, Bernd. It was a pleasure to have you here. And we will now move to the second talk. So we will need to switch back the screen to power. And the next invited talk will be given by Raquel Otasun. Raquel is the Uber ATG chief scientist and the head of Uber ATG in Toronto. She's also an associate professor in the Department of Computer Science at the University of Toronto and a Canada Research Chair in Machine Learning and Computer Vision. Before joining University of Toronto, she was assistant professor at the Toyota Technological Institute at Chicago, TTIC. And before that, she received her PhD at EPFL in Lausanne in 2006 and did her postdoc at MIT and UC Berkeley. Raquel really brings a unique perspective to this workshop as somebody who actually builds self-driving cars and who has to deal with all the many problems that make perception and tracking difficult in such real-world traffic scenes. So we are very curious and very happy that she volunteered to give a talk, very curious what she has to say. Unfortunately, since she couldn't attend in person, she has given us a pre-recorded video. So we will not have the regular possibilities to ask questions live, but we will collect the questions that you ask in chat or on YouTube and forward them to her, and perhaps she will find a way to answer you. So we're happy to start the next talk now with Raquel Otasun.
Hi everyone, my name is Raquel Otasun and I'm the Chief Scientist at Uber ATG, as well as a professor at the University of Toronto. Today, I will talk about the role of tracking in self-driving vehicles. The traditional software stack for self-driving is composed of a set of modules executed one after another. Every fraction of a second, the vehicle senses the environment. This is illustrated here with a bird's-eye view of the LiDAR point cloud. The first task is then to localize the vehicle with precision of a few centimeters. This is done not only to route the vehicle to the desired destination, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene, here depicted with rectangles for vehicles and circles for pedestrians, which composes not only detection, but also tracking. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as friction and simplistic vehicle dynamics. This full process is then repeated every fraction of a second, typically 100 milliseconds. So given that this is a workshop about tracking, let's focus on that specific part of the stack. In autonomy, tracking is concerned with explaining the paths of the actors in the scene, be it vehicles, pedestrians, cyclists, or other types. In the video, this is illustrated with a consistent color across time for each individual actor. Tracking allows us to extract key features from actors such as velocity, acceleration, and turn rate, which in turn informs us of their potential intentions in the future and allows the self-driving vehicle to safely plan accordingly. Even though as humans are remarkably good at visual tracking, being one of the very first skills we develop as infants, it is a very difficult problem in the computer vision community. In the context of self-driving cars, we are interested in tracking multiple objects. This is typically approached with a tracking by detection framework. First, we detect objects in each frame individually. Then associate detections that refer to the same physical object across time to form trajectories. And lastly, refine their state across time in order to minimize the detection noise and produce trajectories with realistic motion. This therefore characterizes a problem with continuous aspects pertaining to box regression and motion modeling, as well as discrete aspects of data association across time. So let's start there. The discrete portion of tracking covers how to decide that a set of detections refer to the same physical object and should thus be associated. This can be done greedily by immediately associating each detection with the best pair. This is very fast and simple, but often leads to non-optimal solutions. Alternatively, we can formulate the association of pairs as a decision matrix and find optimal assignments using the Hungarian method. This is also a fast and simple method with the benefit of local optimality. To achieve global optimum, we can formulate tracking as an integer linear program describing all the frames, not just two. To achieve global optimality, we can formulate tracking as an integer linear program. And this allows us to find optimal assignments over the entire optimization window, while typically still being fast enough for real-time applications. In the next slides, we will discuss the formulations for this approach to tracking. The formulation of the linear program is done using a minimization over unary and pairwise costs. In particular, the unary costs are typically related to decisions such as, is there a detection, is this detection a real object or not? In here, for instance, we have very good evidence that this is a true positive. But here we have a poorly fit box with very little overlap with the real vehicle. We ideally want to use the first detection, but not the second. We also need to decide if an object does not relate to any previously seen object, and thus defines a new trajectory. We see here an example of a vehicle just coming out of occlusion and into the scene, so likely an object we haven't seen before. Whereas here we have a vehicle that we have tracked for an extended period of time, as it is right ahead of us and in full view. So certainly not a new trajectory. Conversely, we also need to establish when an object defines the end of a trajectory. Here we see an object going out of view, thus ending our observations of it. While for this one, we are still likely to see it next, since it's neither leaving the scene nor close to occludents. On the other hand, the pairwise terms are generally concerned with the associations of objects. In this example, we have two vehicles that are roughly in the same location and share similar appearance features, so very likely the same physical objects. Whereas in this one will have to admit a physically invisible motion to consider them as a match. We need now to formulate these intuitions into an optimization problem that we can solve. To that end, a set of variables are introduced in order to indicate the discrete choices we discussed before. In particular, we have yi indicating that I is a true positive, y new I for I defining a new trajectory, and y end I for when it is the end. And lastly, we have y link ij when I and j are the same object. With those, we can then define the cost of a trajectory as the sum of the individual assignment costs. We have a cost for treating all detections in the trajectory as true positives, a cost for starting the trajectory at the first detection, a cost for associating all detections in the trajectory, and lastly, a cost for ending the trajectory. This gives us a total tracking cost as sum of the individual trajectory costs. However, this does not define a proper optimization problem, since the set of all trajectories, indicated here as calligraphic T, is what we want and not known a priori. So how can we solve this? Naturally, we need to define the problem in terms of units we know, which is in this case are the detections. However, we need to be careful here to produce valid tracks. So we constrain our optimization to produce non-overlapping trajectories, which we express in this set of equalities. First, if a detection I is marked as true positive, then it must, by definition, either start a new trajectory or associate to a previous detection. And it must also end a trajectory or associate it with a future detection. This thus guarantees that all detections will have a valid set of assignments and no two trajectories will share the same detection. With these definitions, we can finally describe a full linear program that we can optimize and find trajectories by minimizing the sum of all the costs subject to the constraints. This describes an offline process that, given a finite amount of observations, produces trajectories that optimally explain them, subject to our costs and constraints. However, for our application, what we really want is online tracking, such that whenever a new observation comes in, we can immediately produce trajectories with what we have seen before. This poses a challenge since the cost of the optimization will grow with the amount of observations and quickly become infeasible for real-time applications. Instead, we can find near-optimal trajectories by solving for a bounded window length while reusing the computations from previous windows. You can look at the paper below for more explanations, as this is a particularly involved piece of work. We can also explore the use of neural networks to predict these individual costs and ways to train them, such as the inference process produces trajectories that are as close as possible to the ground truth, allowing us to leverage the vast amount of data we collect. This is possible through a max margin loss. For this, we first run a detector over our input to produce detections, then run another set of neural networks to predict individual tracking costs, and optimize the linear program. If we then take the ground truth into account, here shown are as the shaded green box, we see that our detections were not very well aligned. And thus their assignment costs should be increased a bit. Let's assume these are our only two frames. Then certainly this detection defines a new trajectory, and so the cost should be reduced. And conversely, this defines the end and should also be reduced. Lastly, we have a pair of weakly fit detections, but they still reasonably refer to the same object, so it seems appropriate to reduce their matching cost. These increases and reductions in cost allow us to compute gradients that we can then use to update the weights in our neural networks via backpropagation. To find more details on this approach, we refer you to our paper in the footnote. We have thus defined a way to train neural networks to produce a stream of frames, first extracting individual detections independently, and then optimizing over the entire window to find trajectories. This process by itself, however, cannot correct noise from detectors, which are typically trained to regress boxes that produce the best fit for the specific frames they receive, not temporal consistency or smoothness, and associating these sets of boxes will not change that. If we, for instance, plot the angle of the vehicle as it makes a turn, we can see that our raw observations follow a noisy curve when compared to the ground truth and don't produce a realistic model of motion. Having a kinematic model is key here, as we can mathematically describe them with differential equations and adjust our observations such that they conform to the model. This is a framework that allows us to use our creativity and prior knowledge about the world to create models that follow unexpected behavior, for instance, constant velocity or turn rate and acceleration. Furthermore, we can also use different models for different actor types, since the kinematics of a pedestrian is largely different from those of a vehicle. We can go further and take the uncertainties of the observations into account by modeling the involved probabilities. This is typically done with statistical inference approaches such as Kalman filter, which models the covariance in the continuous state space, or a particle filter, which then models the full distribution. We can also take another step and model our classification uncertainty, allowing the filter to switch motion models in case we misclassify a cyclist for a pedestrian, for instance. Lastly, we might also be able to take a fully learned approach to this using recurrent neural networks. In a traditional self-driving pipeline, predicting how the objects will move in the next few seconds comes after detection and tracking, since tracking is really not the end of the full stack. The simplest method to try to tackle this problem is to enroll the tracker state with a kinematic model, such as a constant velocity or constant turn rate and acceleration. However, we can see in the cartoon that if we have a vehicle right before making a turn and showing any angular velocity, both kinematic models will fail to predict accurately. Another option is to perform maneuver-based prediction. This is a two-step method. First, the intent of the actor is classified, and then we can either use a fixed set of prototypical trajectories for each intent, particle filtering, or other approaches to obtain the final trajectory. The main downside with this traditional pipeline is that the information that gets passed into prediction and about detection and tracking, as well as the static environment, is very compact and handcrafted and makes over-simplistic assumptions about uncertainty, causing information loss. To fix this, let's see how more recent works have tried to use neural networks to learn more flexible representations. There are many representations that were originally designed for detection that can be used for the task of motion forecasting. Waypoints of past trajectories, together with their uncertainty, if available, can be passed through an RNN encoder. Some works have also leveraged voxelized LiDAR in a local region around the perceived actor to account for geometric cues. A better option is to rasterize the geometry of the perceived traffic participants in a multi-channel, bird's-eye view image local to each actor, and use a CNN on top of that to extract actor features. For the environment, map rasterizations have also been explored. Recently, approaches that exploit the relational information in the map together with graph neural networks or transformers have also been proposed. Our lane graph net model outperforms the state-of-the-art in the Argo-Verse motion forecast benchmark. Importantly, our result was submitted 3 months ago to the leaderboard, and it still has the best multimodal minimum average and final displacement error, despite the fact that there was a competition in between with prices. While this great performance is exciting, the Argo-based dataset assumes that the input to the prediction system is perfect perception, which is never the case in practice. If we look back at the traditional software stack, the advantage is that we have interpretable representations, and it is easy to incorporate prior knowledge. However, this traditional engineering stack has also many disadvantages. For example, reaction time is typically large as competition adds up. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for these changes. Furthermore, the different models are not trained for the end task, and thus improvements in model performance do not translate to better driving. Instead of assuming the perception information is correct and that a compact representation can capture all details, Can we instead learn a shared representation valid for the two tasks? This will lower the reaction time, produce richer representations thanks to joint optimization, and we will still preserve the interpretability of both tasks. Our work Fast and Furious was the first to show that it is possible to unify both tasks. The input is a history of previous LiDAR sweeps. Using the pose of the SDV at different timestamps, we can project past sweeps to the current coordinate frame. We can then voxelize the point clouds into a bird's eye view tensor with 4 dimensions: height, width, time, and depth. Now we can run 3D convolutions using depth features to fuse spatiotemporal information. Once the time dimension has been reduced, we can predict the outputs with 2-dimensional convolutional headings. For each pixel in the output map, Fast and Furious predicts a classification score and a series of future waypoint regressions. To obtain the final detection, we threshold the scores and apply an NMS as usual in object detectors. We then obtain a single feature trajectory for each actor by indexing the regression tensor at the positive locations of the classification after NMS. Fast and Furious also included tracking, but as a post-processing. The idea is that since we have the information about previous motion forecasts outputted by the model at early timestamps, we might as well use this information for tracking. In this fashion, the bank of tracks not only contains information about the most recent track states of the vehicle, but also the latest motion forecast. When detections from a new timestamp are available, we can compare this to the new motion forecast, to the previous motion forecast, taking into account the time difference to get a match. In this case, we use a simple heuristic that works well in practice. That is, we associate each detection to the previous forecast with highest overlap if bigger than an IOU threshold. For each association, we heuristically update the confidence of the track and the motion forecast. If a detection does not have a match, we create a newborn track. Finally, if a track is not associated with any detection, we heuristically decrease its confidence and discard it when it's below some threshold. In this video, we show the LiDAR point cloud together with the detection scores, bounding boxes, and the short-term motion forecast for 1 second into the future. The vehicles are color-coded according to a heuristic tracker that I just explained that matches the detection to previous motion forecast in a post-processing step. Notice how difficult the problem of self-driving is, how many actors we need to detect, track, and predict its motion into the future, and how well this approach works. Maps are an important prior for both detection and prediction. For instance, it is more likely to find a vehicle on the road than in the sidewalk. And we know it is likely that a vehicle keeps its current lane in the future. Our work in TENNET proposed to raster the map in bird's eye view and extract features with a 2D CNN, which can then be trivially fused with the LiDAR features coming from the other streams by concatenating along the feature dimension. Here, the LiDAR CNN is simplified to a regular 2D CNN by stacking depth and time together in the input, which yields better performance and is more memory efficient. Moreover, in this work, we show that we can also accurately predict discrete intentions by adding yet one more header that performs multi-class classification over actions such as turning right, stopping, being parked, or lane changing. This allows the planner later on to not only reason about occupancy, but also about semantics and recover the interpretability of traditional approaches to prediction. The outputs of the network are split here into 2 visualizations. On the top, we can see the same outputs as in Fast and Furious, and in the bottom, we show the high-level action prediction, which provides a more interpretable way to see the driver's intention than just future trajectories. More precisely, this gives us the probability of a car being parked, stopping, keeping lane changing, or turning. A purple bounding box means our model believes the vehicle is parked. In the spectrum below yellow and red, the redder, the higher the probability of stopping. We visualize the likelihood of keeping lane, turning, or lane changing by the length of these arrows. Just as an example, we can see here that the neighbor is very confident with a lane change is taking place. You can see here the wide variety of scenarios and the difficulty of the task. However, the single-stage architecture of previous PMP models, although very fast, is not very flexible. For instance, we cannot reason explicitly about active interactions, since the notion of an instance is only recovered after object detection. But these methods predict detections and motion forecast in parallel. Therefore, next, we change the architecture to a two-stage approach, where the motion forecasting model reasons at the instance level. To do so, we first extract features from LiDAR and maps just as we have done before, and fuse them. Once we have rich features from the whole scene, we can obtain object detections shown in red. Let's focus on one of the vehicles. Since we know the information ahead, and to the size of is the most relevant, we attribute this region of interest to the actor. Then we can pull the features on that region as the summary of the actor characteristics. We can do this process for all vehicles in parallel. We can now further process the features with a CNN with global pooling and obtain a feature vector for each actor, which is passed to the prediction mode. In the results we're going to show next, we evaluate different approaches in the challenging ATG dataset, which is basically composed of many scenes that have been driven around multiple areas in North America. And they have very complex scenes with many, many actors, making it very interesting for agent-to-agent interactions. Most approaches to motion forecasting assume perfect perception in their papers, or in other words, that the ground truth path trajectory is given. As we all know, this is not realistic in self-driving cars, where we must operate with a real noisy perception system. We see two options to use them in the real world. The first one is to keep their method unchanged by extracting past features using an off-the-shelf tracker that consists of an interactive consists of IMM with unextended Kalman filtering and concurrent matching on top of the detections in the past frames. The second option is to replace the past trajectory encoders in these methods with our feature extraction pipeline and train the model end-to-end as a joint PMP model. We take three public methods that assume perfect perception: social LSTM, convolution social pooling, and CARNet, and we implemented these two versions of them. Tracking base, shown in blue, and end-to-end joint PMP, which doesn't have tracking, shown in red. We can see that the PMP adaptation of these models brings a big improvement over the traditional pipeline based on tracking that is not optimized jointly. In particular, we see reductions of an order of magnitude in the collision rate among predicted trajectories from different actors. This shows that the initial hypothesis that the traditional pipeline passes too compact of a representation to prediction is actually true, and that optimizing end-to-end yields better results. One aspect that is hard to handle from the traditional pipeline is missing data, which we encounter when either a vehicle was not detected in the past or the track was fragmented. A natural question is, can we bring tracking to the joint perception and prediction framework? This is exactly what PMPNet does, which is a new framework for joint perception and prediction that brings object tracking in the loop. Specifically, PMPNet performs detection, tracking, and prediction subsequently. For tracking, it solves both the discrete problem of data association and the continuous problem of trajectory estimation. To keep track of objects across a long time horizon, our model has an explicit memory that memorizes the past tracks, as well as their features. Given object trajectories produced by the tracker, we also propose a new trajectory representation that captures both the frame-wise observations and object motions across time. PMPNet is end-to-end trainable and benefits from multitask learning. Here we illustrate how to build a PMP model step by step. We start with a joint perception and prediction model without tracking, where we have a bird's eye view backbone network that takes the raster images of multi-sweep LiDAR point clouds and HD maps as input, and outputs object detection as well as their corresponding feature trajectories. This model will serve as the baseline for PMPNet, and from now on, it's going to be referred to as baseline. Now we add object tracking to the model after object detection. We first add a discrete tracker that associates objects across time in an online fashion. Note that our discrete tracker also handles newborn and occluded objects, as these are important for self-driving safety. After object tracking, we get a set of updated object tracks. We then add a continuous tracker that smooths these trajectories. This step has the potential to correct errors made in discrete tracking or object detection. After discrete continuous tracking, for each object we extract its past trajectory feature and use that to predict the future trajectory. Note that this differs from the baseline model, where motion forecasting exploits the features from the current frame only. To keep track of objects online and for a long-term time horizon, we equip the model with explicit memory of already tracked objects, memorizing their trajectories as well as their features. This enables our model to recover objects from long-term occlusions with real-time state estimation. Before we go into details of the proposed discrete continuous tracker, we first define how to extract the trajectory level representation. This representation is used by both the tracking and prediction models. Given an object trajectory, we first extract a history observation feature, which is defined as a concatenation of object observations at each timestamp. Note that the past VAV feature maps are already saved in the memory. Therefore, the feature computation here involves query operations only, which is done as bilinear interpolation of the object-centered pixel feature. In practice, rotated array pooling can also be used. Apart from the observation feature, we also extract the history trajectory feature, which explicitly encodes the object motion. Specifically, the trajectory feature is defined as the local displacement of object-centered positions and orientation in bird's eye view. Given two types of history features extracted, we then merge them frame by frame and extract temporal context by feeding the sequential feature into an LSTM module, which outputs a fixed dimension representation for the trajectory. We choose LSTM for its capability to handle variable length of input data and the ability to capture long-term dependencies. Now we give details of our discrete continuous tracker. We first introduce the discrete tracking, which solves the data association problem between past tracks and current detections. For each past track, there can be two association results. It either finds a success match with a current detection, or does not find a match, and therefore we assume it is currently being occluded, as we have to hallucinate its current state. Note that this is important for self-driving, as we need to pay attention to occluded areas in case traffic actors come out of it. For each current detection, it also has two different association outcomes. It either gets associated with a past track or does not, which means that this is a new object coming into the scene. The second case happens a lot in self-driving scenarios, as the ego car is moving as well. To cover all different outcomes in data association, we combine the benefits of both multi-object tracking and single object tracking. Specifically, multi-object tracking solves for the exclusive assignment between tracks and detections, including the newborn of tracks. Single object tracking, on the other hand, solves the state estimation for unassociated tracks. Next, we explain how we approach multi-object tracking and single object tracking, respectively. We first build a bipartite graph composed of past tracks and current detections. We add the same number of pseudonodes as detections in the track side of the graph to account for newborn objects. We compute pairwise match scores using learnable matching functions. Specifically, we use an MLP that takes both trajectory and detection features as input and outputs a scalar value. We use the Hungarian algorithm to solve for the optimal frame assignment. In the case shown below, we find associations for 2 out of 3 past tracks, with 1 track unassociated. There is also a newborn object here. After multi-object tracking, we then perform single object tracking on unassociated tracks to estimate their current state. Our model design is similar in spirit to the CMS tracker, but replaces the correlation filter with a learnable matching function. In particular, we find a neighborhood in the current frame's VEV feature map, centered at the previous frame object position. Each voxel in the neighborhood is considered as a candidate. We then compute the match score for each track voxel pair with an MLP, given the track feature and voxel feature as input. We find the best candidate by using the Rmax over all matching scores. We argue that compared with simply adopting a motion model for state estimation, our single object tracking approach can produce more accurate estimation as the current observation is exploited to provide helpful information like the map context. For each updated track from discrete tracking, we re-estimate its confidence and smooth the past trajectory. While the first step helps remove false positives from object detection, the second step helps recover association errors made by the discrete tracker. Lastly, we apply NMS to remove duplicated tracks that are highly overlap. The motion forecasting model of BMTT is a simple regression-based feature prediction. In general, more complicated prediction models can be applied here as well. The key to the success of the motion forecasting model is the enriched input feature, which is defined as the trajectory representation after discrete continuous tracking. Note that this differs from our baseline model, where the prediction header shares the same voxel feature as at current frame as the detection header. Here we explain how we perform end-to-end optimization of the whole model. We apply multitask loss for detection, tracking, and prediction respectively. For detection, we use the conventional loss function, which is a cross entropy for classification and a smoother one for regression. For discrete tracking, we apply max margin loss on the affinity matrix. For continuous tracking, we apply max margin loss on the confidence scores and a smoother one on the trajectory refinement. For motion forecasting, we apply a smoother one for feature waveform regression. Since our model involves strong temporal dependencies, we adopt video-centric training, where we sample video snippets from the training logs as a mini batch, and during training we use online estimations instead of ground truth. Instead of ground truth labels from previous models and timestamps, so that we fully mimic the test time situation. Here we show the results of BMTT in terms of 3D object detection on the nuisance benchmark. We evaluate car detection and show from the table that the detection model of BMTT achieves state-of-the-art performance compared with other 3D detectors. We now look at the tracking results. We achieve 8% gain on the ranking metric MOTA compared with the state-of-the-art method on the benchmark. We then replace the discrete continuous tracker with a Kalman filter-based tracker and still show a 4.6% gain in MOTA. What's more, BMTT also produces more complete trajectories, which is justified by the few SID switches and fragmentations. We also showcase better occlusion recovery capability with more quicker tracks initialization time and much smaller gap duration. Now we showcase the joint PMP results. We show perception metrics in the left plot with detection AP and recall rates, and show prediction metrics in the right plot with prediction ADE and FDE, which corresponds to trajectory waypoint offset average over the future 3 seconds and at the endpoint. We plot relative improvements over the baseline model that doesn't have the tracking model. On nuisance cars, we show a 2% gain in detection AP and up to 4% improvement in object recall, which mainly comes from occlusion recovery. Thanks to the enriched trajectory representation, we observe up to 9% error reduction for prediction errors. When we apply our model to another dataset, ATG40, with different hardware settings, similar improvements on perception are achieved. We observe a large improvement on prediction with up to 16% error reduction. This is because ATG40 contains a larger proportion of moving vehicles compared with nuisance. Therefore, the gain of exploiting long-term history is more significant. In addition, to validate the generalization across datasets, we also test BMTT on pedestrians, where similar gains are achieved in both perception and prediction as well. The results show that the fully learnable trajectory representation and the matching function can successfully learn from data different motion patterns. Here we show some qualitative results of BMTT on vehicles and pedestrians within 100 meters in ATG4D dataset. Our model is able to produce scalable tracks, even under occlusion, and produce accurate estimation of future trajectories. To summarize, we have seen that neural networks can be trained end-to-end to do detection and tracking. However, for self-driving, we ultimately care about occupy the space now and into the future in order to plan a safe maneuver, and this might change the whole game. To address this, we perform joint perception and prediction, which we have shown works better than the traditional pipeline where detection, tracking, and prediction are conceived as sequential and are optimized separately. Finally, we have shown how we can add the tracking in the loop for our end-to-end differentiable framework, achieving the best results. This is all for me today. Thank you.
So thank you very much to Raquel Utterson for agreeing to give this very nice talk. As I announced before, she's unfortunately not able to be here in person. So that means we can't directly ask her questions. And therefore, we can move on to the next item on our agenda, which is that most of you have probably been waiting for, namely the results announcement.
Okay, so I hope my screen share is working again.
Yes, yes.
Good. Okay, so let's jump directly into it, since we are already slightly behind schedule, I think. So here are the results for track 1, which was multi-object tracking and segmentation on the MOTS 20 dataset for pedestrians. So we had 10 entries here, and the results span from 51 MOTS score to almost 70. So quite a big range covered. And it's also much stronger than the baseline we introduced together with the dataset, which is not shown in the table here now. And the winner was MOTS with 69.9 MOTS score, which is a very strong result. However, their method is not extremely fast so far, but there is also other methods with different speed accuracy trade-offs. And I'll be curious to see soon the presentation of the winner. But first, let's look also into the results of track 2. By the way, thanks for everyone for participating and congratulations to the winner. So track 2 was on the Kitty MOTS dataset. Here we had 9 submissions, and tracking and segmentation had to be done both for cars and pedestrians. And the total score by which the results are ranked was the average of the SMOTS score of cars and the SMOTS scores of pedestrians. And here also GPS and LiDAR could be used. And the method PointTrack++ achieved the highest result with a score of more than 75. And here we can also see that the result for pedestrian is quite a bit worse than for cars. So it seems pedestrians are more challenging. But this could also be because there is much less training data for pedestrians here, because cars are more represented. So also here, thanks for everyone who participated. And congratulations to the winners. And also there we'll soon see a presentation from the winners. Okay, so there was a slight mix-up on the schedule that we wrote on the schedule that first track 2 will present and then track 1. So if the presenters for PointTrack++ are here now, I would suggest that we start with them.
Can I share mine?
Yes, sure. I will. Okay, I will close my screen share and then you can give your talk. Thanks.
Is the PPT okay for everyone?
Yeah, it looks good.
Okay, let's get started. Hello, everyone. My name is Zhang Wei from the Department of Computer Vision Technology of Baidu. Here I'm going to introduce our recent work entitled PointTrack++ for effective online multi-object tracking and segmentation. As we know, MOTS is the first task that jointly considers two challenging tasks. First is the instance segmentation, another is the multi-object tracking. Traditionally, in MOT, we usually implement 3 stages. First one is the bounding box detection. Second is bounding box-based feature extraction. And the last one is to associate different bounding boxes across the frames. Differently, for MOTS, we are required to first finish the instance segmentation. Then we should do the feature extraction based on the mask instead of the bounding box. And finally, we also do the association to finish the tracking. In this work, we are going to we are trying to answer 2 questions. The first one is how to efficiently do the instance level segmentation, while the second one is how to extract the MOT-oriented instance embedding from the object mask. Actually, we have 2 versions of our pipeline. First is the base version named point track. The second one is an improved version. We name it point track plus. We use point track plus in this challenge. Next, I'm going to briefly introduce point track. Then later on, I will introduce the difference between these 2 frameworks. In point track, we adopt spatial embedding as the instance level segmentation network. Sorry. Spatial embedding is the state-of-art one-stage instance level segmentation network. Thus, it runs very fast, and it's faster than the 2-stage ones, such as the MOTChallenge. In spatial embeddings, the architecture is basically based on encoder and decoder network. It has 1 encoder and 2 different decoders. 1 decoder is for predicting a seed map, which is trying to find the center of each instance. Another decoder is to predict a sigma map and also an offset map. Finally, a grouping strategy is used to generate the instance segmentation results. In the inference stage, of the spatial embedding, we use a 3-stage recursively to group the pixels and generate the instance mask of each instance. First, in the first stage, we pick up the pixel with the highest seed score as the center of the instance. Then we group pixels according to the offset and sigma. Specifically, the offset vector is used to predict the offset vectors, which points to the object center, while the sigma determines the instance-specific clustering bandwidth. In the 3rd step, we just remove the pixels from the seed map, which has been already grouped. These 3 stages performs iteratively until all the segments and the pixels are grouped. Besides, in the original spatial embedding, since the original embedding is just based on the image, we further improve the spatial embedding by introducing a temporal coherence loss for the seed map to improve its performance on the video streams. Okay, sorry. Next, in the feature embedding stage, one common choice is to choose the conventional convolutional neural network-based methods to extract features. However, this standard layered of convolution networks will usually mix up the foreground area and the background area of each instance. Secondly, it usually mixes up the foreground area of the instance and the adjacent instances. Both of these 2 points can be expected very harmful for high-quality feature embedding training. In contrast, ideally, the foreground area and the environment area should be well separated during the training. And it is very important to learn discriminative features to differentiate the spatial adjacent tracking IDs during MOT tasks. So considering above issues, we propose to regard image pixels as unordered points instead of 2D rigid pixels. In this way, we can sample points in the foreground and environment areas respectively. Based on this strategy, we further propose to extract features for foreground and environment area, then combine the features together as the feature for each instance. Next, I'm going to briefly introduce the embedding network that we proposed in point track. Given one instance segmentation map, we regard the foreground pixels and also the environment pixels as 2 separate point clouds. Then we sample points from these 2 point clouds separately. For each sampled points, we use 3 different kinds of features. One is the offset. The second is the color, and the third is the category of this pixel. By combining these 3 kinds of features, we use the combined feature as the input of the feature extraction network. Our feature extraction network is designed inspired by the point net, which is basically a point-wise processing network. Using this proposed feature extraction network, we can extract the 3 kinds of different feature embeddings. One is the MF, which stands for the foreground embedding. The second is the environment embedding. The third is the position embedding. Afterward, we combine these 3 kinds of embeddings to learn the final instance embedding M for each instance. In the tracking stage, we simply use the Hungarian algorithm to perform the association. Let's see the results of point track. Using our proposed point track, we achieve state-of-the-art performance on the Kitty and MOTS dataset in nearly real-time speed. Next, let's move on from the point track to point track plus. In point track plus, we further introduce 3 improvements. The first one is we use semantic segmentation map as the seed map. Secondly, we introduce a copy and paste strategy for data augmentation, especially for the instance segmentation training. for the pedestrians. Thirdly, we develop a multi-stage training strategy for the instance embedding network. Let me briefly introduce them one by one. In the point track, we use the Gaussian heat map as the ground truth of the seed map with the L2 loss during training. In contrast, in the point track class, we change the Gaussian heat map to a binary semantic map for each class and adopt a focal loss during training. Secondly, here is the visual results of the segmentation seed map and the semantic map. As we can see, both the false negative and the false positive can be greatly reduced. Secondly, we developed the copy and paste strategy for the data augmentation. We observed that the original spatial embedding is not good at learning stable masks for the pedestrians. One reason is the occluded samples are relatively rare in the KDM and OTS dataset. So we manually we manually increase the density of the instance in the training set by copy samples from other training images to the training image. Thanks to the high quality annotations of MOTS dataset, this copy and paste strategy can be done very conveniently. Here is one more visualization results of the point track plus and the point track in terms of the segmentation quality. As we can see, point track plus in the last row greatly improves the quality. Next, the final point is the multi-stage training strategy we developed for instance embedding. In the training stage of instance embedding, we sample 3 crops from different frames for each track ID. However, in the original point track, these 3 crops are sampled using a randomly selected interval. We use 1 or 12 frames as the interval during sample. Recently, we find out that 12 interval framing as interval is too large for the training because both the background and the location of the samples changes dramatically. So in point track plus, during the training, we set different frame intervals for different kinds of for the training of different kinds of features. Specifically, we set 8, 2, 1, and 5 interval frames for the training of MF, ME, MP, and the final feature embedding M. We choose these interval frame numbers empirically. During the training, we adopt triplet ranking loss with online bench hard triplet mining strategy. Here we provide the results on KDM and OTS validation set and also the testing set. As can be seen, point track plus improves the final results both in the category of cars and pedestrians. In this table, we provide the evaluation study of the modifications that were made in PointTrack++. In this table, 2x stands for the upsampling strategy during the training of the segmentation network. SEM represents the strategy of using the semantic segmentation map instead of the seed map, instead of the Gaussian heat map for the training of the seed map. CP stands for the copy and paste strategy, and the SEP stands for the separate training strategy for the instance embedding we mentioned previously. As we can see, both this, all of these 4 modifications contributes to the improvements, especially for the pedestrians. Here is the video of the results of our proposed PointTrack++. We visualize the tracklet belongs to the same ID using the same color. Basically, we can generate very good results using PointTrack++. Finally, is the conclusion. First, we propose a novel online MOTS framework named PointTrack. Secondly, we propose a novel MOT-oriented instance feature embedded method. And finally, in this challenge, our proposed PointTrack++ achieve some improvements of the baseline version. Thank you.
Yeah, thanks for your nice presentation. I think these were pretty impressive results, and especially the qualitative results look quite solid, I would say, at least for cars. Pedestrians were only partially covered there, but I'm quite happy about this level of results which we got now for the competition. Are there any questions for the speaker? Okay, it seems we don't have any questions.
If not, we will have an interactive session after the next talk. So if any further questions come up, they can be asked in that session.
Okay, so next on the schedule will be the oral presentation for the track 1 winner, which was a MOTS 20 dataset for pedestrian tracking and segmentation. And there, the method was ReMOTS, refining multi-object tracking and segmentation, by Fang Yang and his collaborators. So I hope you are here now. If yes, please share your screen.
Yes,
and
could I share my slides?
Yes, of course.
Okay. Yes, it's everything. Everybody can see my slides clearly.
Yes.
Okay, let me start. Hello, everyone. Thanks for having me here. My name is Fang Yang, a student of Nara Institute of Science and Technology. I'll introduce our solutions, which named ReMOTS, refining multi-object tracking and segmentations. So first, let's go around the background of MOTS again. The problem is to detect, segment, and track multiple objects in videos. The input is a video sequence with the RGB images, for example, like this one. And the output will be 2D mask and corresponding ID at each frame. Compared to instance segmentation, we want to associate cross-frame objects, assign the same identity, the same IDs. And of course, there are plenty of applications like action recognition, or automatic driving, and others. So the first step to approach this we need to do instance segmentation. For this step, we do not have a very good idea, maybe like a previous point track. We just take over-the-shelf models. What we use is like we use 2 models from detection, detection 2, and then we'll try to fuse the result together. So how to fuse them? We think fusing the mask is a little different from fusing the boxes. Fusing the boxes, we can just simply use the NMS, but fusing the mask, maybe we suppose we need to change a little more from the IOU to IOM, which means intersection over minimum. What does it mean? For example, we have 3 masks here. The number represents its width and its height. So let's say 2 masks have an intersection here. If we calculate the pixel IOU, it will be approximated by 0.33. However, for this blue one and this green one, this kind of pixel IOU is quite small. So if we use the traditional NMS, maybe we'll just include the above one, but keep the bottom one. However, as we know, the bottom one is not so correct. It's acceptable for the bounding box, but not for mask. We should remove all the overlappings in the mask. So therefore, we change from the pixel IOU to pixel IOM. If we change to IOM, only calculate the minimal overlapping areas, we might find in the bottom case, the pixel IOM is approximate to 1. Therefore, we might exclude the bottom one instead of the above one. This is a method we use to fusing different models. However, our main focus is the second step, that is to associate the mask across the frames. Our main contribution is refining appearance features step by step and automatically deciding the threshold instead of heuristically setting them. We propose a method and the refining MOTS, but it is an offline method. Give an example here. First, we have 2 frames, frame K and K plus 1. And the green box and this blue box only exist in frame K. So in next frame, we'll simply copy paste the location and paste in the next frame. We might see some overlapped objects here as this new existing purple and the green and the blue. So we're only considering this object in the next frame, which have IOU larger than 0s, and use them to calculate the appearance features. The appearance feature model will take our existing model from the Bagel-Tricks, which is a published TMM paper. But we did something special here. It's our training strategies. We said if we only use the trainings like the traditional one, only use the training in the training data, it might not well adapt to the testing videos. Therefore, we want to include the unlabeled testing videos in the training. Suppose for the training set, we have the ground truth. We can directly sampling the positive sample and the negative sample for anchor sample. However, for the testing videos, as we already applied AMS, we suppose 2 samples which have no overlap, they should be different IDs in the same frame. Therefore, we can easily construct a negative sample by sampling different samples from the same frame. For the positive sample, we might think our augmentation might help us to do this, although it's not so good as using the ground truth, but generally it might help to do this kind of triplet training. We build a mini batch by the ratio 1:1 and use for the training the appearance coder. Then we get the embeddings and then calculate the appearance distance and do the assignment. For all these places which IU plus than 1, equal to 0, we assign them to infinite, but plus for one place, we keep the original coordinate distance and use linear assignment. One thing to mention here is like when we look at the intra-frame observations, the coordinate distance, we calculate the distributions, we found they're almost like Gaussian distributions. Therefore, we want to automatically to decide the threshold for the linear assignment. And we take the 3 standard deviations as this appearance threshold here. Such way, we do not need to heuristically decide the threshold, and we let the data speak for itself. So as we have instance labels here, mask here, we use this kind of simple appearance encoder and just considering 2 cross-frame videos and to generate short-term checklists. So they're not ideal because we do not considering any memory. We're only considering 2 frames. They may break at any place due to the overlap or other issues. But since we use our very strict threshold here, we almost can make sure within the same short checklists, they should keep the same identities. Few noise will be introduced in such way. So we want to utilize this obtained short-term checklist to do another appearance training again. How it makes, just now we only know the frames, the object within the same frame, but now we use the short checklist and can use the pseudo labels to construct positive and negative samples. But we need to take care. We only have to considering the overlap checklists. If 2 checklists are not overlap, for example, like this green one and this orange one, they may still hold the same identities just because we failed to associate them together at the first step. So we have to considering the overlap one. And for the training set, no difference. So this way we construct another batches and do our inter-short-term checklist training to obtain better features. What happened through the 2 steps of training, like intra-frame training and inter-short-click trainings, we do a qualitative visualization to see what happens. Suppose this blue one is intra-frame instance mask, and we'll calculate the causal similarities to put here. This is a distribution, and this is the intra-short-click track-lead one as the pink one. We must see if we only train on the training set only, using the Jakarta distance, Jakarta index to measure the overlappings, we may find the overlapping is quite high. And after the intra-frame trainings, we found we actually decrease it a little. But after the intra-short-click training again, we may almost make it to 0. Notice that such kind of distribution is only considering the short-lived checklist. It's not the ground truth. So because we don't know the ground truth in testing, but at least for the predicted short checklist, we can make sure the different instance and the same different and the same distance instance have been successfully separated. After that, we try to associate the short checklist into the long-term ones. We set some rules to associate them together. First, we use the well-trained appearance encoder to get the appearance features and then put them together to calculate the causal similarity. We also set some rules to exclude impossible cases. Ones with the same identities, like this same track lead, we should not assign them together again. Another is temporal overlapping. As they already overlap together in temporal domain, they might not be the same identities, so they should be excluded. Therefore, we can get this distance matrix again. In this step, we associate them together by hierarchical clustering. Hierarchical clustering is just considering the distance between instances and step by step and groups them into clusters. However, the cutting threshold is very sensitive parameters. It's not so easy to decide it. We make it automatically decided by looking at the distribution again. As we just introduced, we can make distribution about the intra-frame and the intra-short tracklet distributions. As the pink one means there's same identities appearance similarity, and this blue one is a different one. So therefore, we can make a threshold in the center and use it as the cutting threshold to put the short tracklet into the long-term ones. This is our result on the leaderboard. And in terms of this matrix, as it is illustrated here, we may benefit from the mask efficiency. And in terms of IDF1 and MT and ML, our result is relatively good. We think it might need benefit from our refinement steps. At the same time, we also look at other people's solutions, and we think maybe our strategy can be very easily adapted to theirs. For example, also adapt to the previous point track. And maybe other methods can get better performance by just using our appearance training strategy and such kind of merging refinement. Of course, there are some limitations for our method. One thing is our overline approach. It's not so applicable in the real applications, but it worth to explore how to bring the ideas of it to the online approach. For example, like how to automatically decide the threshold or how to do online feature refinement. We might consider it in the future. Another thing is also very challenging for remotes to handle objects with similar appearance. It may be very good for the persons because usually person wearing different clothes, and we can very easily to identify the textures, but not useful for the cars when the car have very similar texture appearance without considering the location and motion. And also, as we introduced, our short-term trackers is so simple. We're only considering two-frame association. The trajectory is not being considered. And it might fail to associate with the fast-moving object like in the KITT dataset. So conclusion, we think the unlabeled target videos can be used for learning better appearance features, but we should really take care of the potential or introduce noise. We think our intra-frame training and inter-shock lead trainings might hope to solve this problem and avoid introduce too much noises. And to make the suitable parameter could be very useful in the data association. And we'll say maybe it's important to get the threshold from the statistical information of the tracklet instead of the heuristically setting and have to test one by one in different videos. And maybe it's preferred to accommodate some of the insight of our method to the online modes and make it more applicable in the future applications. Thanks for listening. That's my representation.
Okay, thanks for the nice presentation. Are there any questions for the speaker? Or maybe let me ask one. So I think you said for future work, you want to think about how this could be done as an online method. But my feeling is, since you are using the test data to train on it without labels, it might be quite hard to actually do this. Do you have any ideas on how this could work?
I suppose maybe like this. Oh, sorry. Like this step, at least when you have the observations, we can calculate. We already have assumptions. Different masks must belong to different identities, even we just get it online, and such information could be utilized. And for the tracklist, if you keep a memory in the past history, such kind of history may just like the short-term tracklet used in our examples like this one, because you might just keep the previous history. Yes. Oh, okay. Have I answered your question? Sorry.
Yes, thanks. Maybe let me ask one more. So, did you also try this for Kitty, and if not, why?
For the Kitty sense, to be honest, it's like I also joined some other competitions, so I do not have too much time to spend on it. I arbitrarily set I use the public detection and maybe choose a not so good confident level to get the MOTS. And I think the result is I sent the track 3, which is the public one, to you. You might see not so good. One thing is like we do not do the last step for the hierarchical association. We do not have this one. And also because in the KTT, in every frame, we may not find too much persons. It's actually a little hard to constrain the refined trainings because we need sampling the instance, but it's not so easy to get a KITT. So due to such kind of reasons, we just use what we trained on this MOTChallenge 1, directly apply in KITT and get the result in the track 3.
Okay, thanks. You mentioned that there were not enough pedestrians, but does your method work the same for cars? Or
for cars, I think it's the issue here. It's like we suppose since many cars that have very similar appearance, it might not so good by directly learn, but purely depend on the appearance features. And also because our short-term trackers do not consider any motion of the cars, when they move very fast, it might be just a fail to track in. So use the public mask, we only get 72, I think, in the KITT car mod.
Okay, thanks. There was one question in the chat. So Tayu Long asked if you plan to make the code open source in the future.
Okay, since this is submit to under review paper, so maybe we'll release the code in the future because this is a work which we just submitted before. Yes.
Okay, thanks. Good, so now we have an interactive session on the schedule where there can be some discussion among the participants. I would suggest that we maybe make a very short break of 3 to 5 minutes so everyone can get some coffee or water, and then we can go on with the discussion. So see you soon in a few minutes.
In the meantime, while we wait, there was a question asked over chat to the speaker of the last talk. And that was, will you make your code open source in the future?
Hello, I think just Paul also mentioned this to me. I mentioned that since this work we just submitted to a conference is under review, so we might release the code in the future, but not at this moment. But I think based on the ideas and the workshop short paper, it's not so difficult to implement it, I suppose.
Okay, yeah, that is good. Okay, so we already have the speaker for the next invited talk in the audience.
Hello.
Hi.
Bastian, will we skip the interactive session due to time, or do we still make a quick run?
Okay, so here we can quickly have an interactive session to collect feedback from the audience, from the challenge participants. So one thing that very much interests us, of course, is now that you've worked on this challenge, now that you have used the results from the MOTS datasets, now that you have used also the benchmark scores, MOTS, for example, from your perspective, how much has this helped you? And are there additional things that should be improved, that are still open here at this point?
I guess to make it easy, whoever wants to say something about it can just unmute and talk, as long as it doesn't get too chaotic.
I think one point is if we can add more training data for the track 1, especially for the videos of the street views containing multiple persons. Actually, we have tried the point track plus in these scenarios, but we found both the spatial embedding segmentation network and our proposed feature extraction network do not have sufficient training data. So we did not use the point track plus in the track 1. Instead, we another team from Baidu used TPM-based strategy. So in next year, we hope to see more training data. It might be helpful. Thanks. It's expensive, I know.
Yeah. Thank you for the feedback. Yes, the data generation was actually quite a lot of work. So here, for that reason, we were only able to complete that in time for the challenge, for the data set that you have seen so far. But we see other data sets also now popping up with this kind of segmentation focus. So we hope that also within 1 year, ready in time for the next challenge, there might also be some additional data sets available so that we can do maybe multi-data set training.
Okay, actually, we also, our proposed point track is also under review paper. In this paper, we actually contribute another data set, a large one. It will be accepted and we will release this data set.
Very good, very good.
Yeah, that's very good to know. So the dataset will also be for multi-object tracking and segmentation, and each frame will be annotated?
Yeah.
Okay, great. Looking forward to that. Okay. Are there any other questions or comments about the datasets, the evaluation measures, or in general how helpful the segmentation masks were compared to just bounding boxes?
Hello, Paul. I have a question about the evaluation matrix. Although I know you offer the public segmentations, but however, the augmented segmentation still contain many noises. And sometimes the final results might be reflected by how well people can filter them or refine them instead of do the data associations. I'm wondering if in the future, the MOTChallenges will offer some very clean and well refined mask, maybe as good as the point track or plus or something else, and directly help people to just evaluate how good they are at the data association instead of maybe the detection will significantly affect the final results.
Okay, so this was mainly about providing better public detections. So I guess you are talking about the third track mainly?
Yes, kind of like that. But I mean, even the public ones, it still contains many noises, and we still need to decide which mask to select based on the confidence level or exclude the overlap ones. So, I mean, this also happened in the MOTChallenge, the bounding box based ones. There are a lot of public detections, but the quality actually are very bad, or like say, there are too many possibilities to selecting from them instead of focus on the data associations.
Okay, actually, I think for past MOTChallenges, there were usually 3 different detectors, and some of them were very old, so the detections were quite noisy and not of good quality. And here I actually specifically choose a state-of-the-art detector, so the X152 from Detector 2. So I thought it would already be a reasonable quality detector. So what exactly do you suggest could be done about this?
Yeah,
you are muted now.
From our perspective, from my perspective, one interesting thing that I took from your question was the idea to use the segmentations to perform further analysis of the results, for further analysis of data association, and that is certainly a very interesting idea to consider for future evaluations. So here we're not sure yet how future iterations of this workshop will evolve, how the MOTChallenge will adapt, because here for that really the MOTChallenge organizers, in particular L'Oréal, will have to another say in the design of the future challenges. But one thing that we've already seen is also that the traditional ways of creating evaluations in terms of MOTA for traditional tracking, that is very limited. Also, we've looked at IDF1, that has some advantages compared to MOTA for some of the problem cases, but it also has some significant limitations. So one thing that we have been looking at actually is what other evaluation criteria could be used. And we have a proposal for that. It's not yet fully at the level where we want to go public with it, but we're preparing a larger paper submission on that. So this is work by Jonathan Luyten, and here hopefully, if this work is validated and peer reviewed, we will be able to talk about that. So the hope is that in next year's challenge, we might be able to use that criterion, which gives it much more accuracy for looking into different details of how tracking and how segmentation actually performs.
Yeah, in general, I'm very happy about this feedback. I think you should mute yourself. So if there are more comments like this, also please send us emails, and we are happy to continue the discussion offline. So I think since we're already a bit behind schedule, we'll have to move on to the next invited talk. So originally we invited Trevor Darrell here. Unfortunately, he couldn't make it, but instead Xin Wang will present today. So Xin Wang is from UC Berkeley, and she is a fifth-year PhD candidate in computer science, and advised by Professor Trevor Darrell and Professor Gonzalez. She is part of the Bear Lab, WISE Lab, and BDD Lab. And prior to UC Berkeley, she obtained her BSc degree in computer science from Shanghai Jiao Tong University in 2015. Okay, so I guess we are all very excited to hear from her now about her work and her presentation.
Thanks. Thanks for inviting me. Yeah, it's unfortunate Trevor cannot be here, and I will try to represent the work we have been doing. So I'm gonna show my screen. Can you all guys hear me clearly?
Yes, we can hear you well.
Okay. Okay. Nice. Hi everyone, I'm Xin Wang, a fifth-year PhD working with Professor Trevor Darrell and Joseph Gonzalez. In this talk, I'm going to talk about motion understanding via heterogeneous multitask learning. This is joint work with folks from UC Berkeley. Real-world computer vision applications often require solving multiple heterogeneous tasks simultaneously. For example, in autonomous driving, we need to recognize the lane markings, drivable areas, as well as tracking the locations of different vehicles. We introduced BTD100K, the largest open driving video dataset with 100,000 videos to evaluate the exciting progress of various image recognition algorithms. Our data was collected by crowdsourcing from different locations in the US, including both the East and West coasts, especially the densely populated areas. The dataset covers various scene structure like city streets, highway, as well as different weather and time of day, which is useful for training models that are more robust under different environment conditions. In BDD100K, we provide 10 tasks with heterogeneous prediction structures, such as panoptic segmentation, drivable area and lane marking detection, multiple object tracking, and the instant segmentation tracking. In comparison to the other popular computer vision datasets, ours provides a large set of videos. Some of the other datasets are also generated by the crowd and therefore closer to the diversity and complexity of the real-world scenarios. However, They usually only provide images in the loose temporal visual information and mostly focus on individual tasks or homogeneous multitask learning. In our dataset, we also provide pixel-level prediction tasks and tracking tasks, covering the study of the major visual recognition problems. If we look at our multiple object tracking subset, our tracking annotation set is significantly larger than the previous standard object tracking and instance segmentation tracking benchmarks. Our data has more instances per image, indicating our scenes are also more crowded and more complicated. This skill change opens new opportunities for research on joint object localization, segmentation, and tracking. Let's first dive into the multiple object tracking task. The existing tracking approaches are mostly built upon matching of the ground truth objects between frames during training. This is huge information loss, but only the ground truth objects matching are considered during training. The tracker does not learn how to match slightly deviated proposals, hard negative proposed regions in the images. Those can be valuable information to build more expressive representation and better performing tracker. We propose quasi-dense matching, which considers matching not only the ground truth bounding boxes, but also the object proposals from the region proposal networks typically used in an object detector. In this figure, the green boxes indicate the object proposals to be quasi-dense samples, which are used for matching between frames. During training, we adopt a joint learning of the object detector and the object tracker. This figure shows a typical two-stage object detector, for example, for star CN. A pair of frames are fed into the object detector, and the region proposals are used as the input to the bounding box head for box classification and localization. For the object tracking part, we design an embedding head, which reuses the same set of region proposals from the detector and performs instance similarity learning through contrastive learning on the instance embeddings. During testing, when a new image comes in, we consider matching it to the previous frames. We first extract the feature embeddings and obtain bidirectional softmax at the similarity scores. Only matchings that satisfy bidirectional consistency have high similarity scores. Otherwise, for example, like vanished objects or new objects, the similarity scores will be low. In this way, the object's association is simplified as finding the nearest neighbor in the learned embedding space. One takeaway is that through quasi-dense matching, we are able to learn more discriminative feature representations that allow us to avoid tedious post hoc engineering after object detection. Let's look at some video demos of our object tracker evaluated on BD100K. Our tracker performs very reliably on crowded city streets. And also here are some examples for nighttime scenes. The trackers are still perform reasonably well on this challenging scenario. Let's take a step back to look at the heterogeneous multitask learning benchmark we provided in BD100K. We support 10 tasks with different prediction structures. The tasks ranging from simple image level tasks to pixel level tasks such as semantic segmentation. Further, we can study instance level tasks as well as their domain adaptation problem. In the video context, we can study the tracking of instances based on both the bounding boxes or the instance segmentation mask. Our experiments on different combinations of the tasks reveal interesting properties of multitask learning. Let's start with homogeneous multitask learning. The tasks really have similar output structures and complexity. Here we take drivable area and lane marking predictions as an example. The two tasks are closely related to each other. When we only have 10,000 images of training data, the lane marking performance can be significantly improved. However, if more training data is available, the task-wise accuracy can hardly improve by multitask learning. For example, during learning, the models with both drivable area and lane marking labels can only improve the individual drivable area task by less than 1 point. This shows that for some basic perception tasks, BD100K already provide enough training examples. We also support multiple settings of cascaded multitask learning. One task can serve as the stepstone of the other. We can potentially see the annotation efforts. For example, it is much harder to annotate instant segmentation masks than bounding box predictions. We can leverage the larger bounding box annotation set as a companion task for instant segmentation. We found that we can dramatically improve the instant segmentation accuracy even without semi-supervised learning techniques we're going to describe in the following slides. We also consider semi-supervised learning for instant segmentation, where the training data has abundant box annotations but only limited mask annotations, given it is more costly to label an instance mask than a bounding box. This model is presented in our CVPR work on learning sequencing propagation for semi-supervised instant segmentation. A motivating example is that the bounding box annotations often statistically provide knowledge of instant sequencing regions, which may allow the model to learn useful shape priors of instances in the same category. Another motivating example is that the pixel relation can often be inferred from low-level semantics, such as color, texture, that allows the pixel annotations to be effectively propagated within the same instance. We propose shape prop, which learns to propagate the salient regions from the bounding box annotations to more accurate instance masks through message pathing. The shape prop module can be easily plugged into the existing instance segmentation framework. It takes in the box detections to obtain saliency activations, and then propagates the saliency regions to obtain more accurate shape activation. The learned shape activation will be fused with the backbone features as input to the mask head for mask predictions. For each pixel in ROI features, which we obtain from the detection branch, we first obtain the saliency regions, as shown in the bottom of this figure. And then the features will go through a set of convolution blocks to have the propagation weights. The propagation weights are then used to propagate the saliency regions of our features iteratively. After we have the shape activation, we will use the reconstruction loss during training. We evaluate our shape prop model on several benchmark datasets, for example, COCO and BD100K. In this table, we show the evaluation results on COCO and their semi-supervised learning setting. We consider two backbone models, fast RCN with ResNet 50 and fast RCN with ResNet 101. In both settings, we observe significant improvements over the baseline methods. For example, with ResNet 50, we obtain over 11 points improvements in AP from 23.9 to 34.4. If we look at the results on BD100K, we also observe similar trends. Our shape prop model is able to improve different type of instant segmentation models, and for example, like retina mask here under BD100K, as well as mask RCN. We further evaluate our model under full supervision setting. Again, on 3 benchmark datasets, we will see BD100K, and COCO, the learned shape representations also bring gains on all those settings. Let's look at some visualizations. This is the visualization on sequencing propagation on BD100K. We can see that a very accurate shape activation is obtained iteratively by propagating the information through the original CNC region. Here are more visualizations. We also conducted ablation studies to show the effectiveness of shape prop. The green boxes show the instant segmentation predictions of masked Gaussian with shape prop on COCO, and the rightmost column shows the predictions of the model without shape prop. We can see that the model with the shape prop can predict more accurate instant masks without missing the boundary regions or the regions inside the objects. Here are some more visualizations on BD100K. We can see that the red box on the bottom right, a person is missing in the mirror if not using shape prop, and both people are correctly segmented when shape prop is using. Further, we take instant segmentation tracking as an example of heterogeneous multitask learning. In most cases, we can simplify the tasks as associating the instant segmentation across 2 frames. We can combine object detection, instant segmentation, object tracking in the existing segmentation tracking algorithms. As we can observe from the table, when we train the 4 tasks together, the AP score improves from 13 to 23.3, obtaining over 10 points improvement. Given semantics tracking is much harder than to label and other auto tasks, it means that we can reduce total dataset construction budget when we consider multiple heterogeneous tasks together. For more information, please check our paper. BTD100K brings new opportunities for studying the important problems of heterogeneous multitask learning. Our experiments provided new observations for optimizing the combination of existing algorithms. We also released the whole datasets as well as the annotation toolkit on GitHub. Please check it if you are interested in more details. Thanks for your attention.
Yeah, I guess I'm ahead of time, and I'm happy to take any questions you have.
Hello, could I ask a question? I saw in the last slide, it seems there's an instance mask tracking challenge for the or data set for the BDDK. Actually, this year I attended the BDDK box tracking. I also won the first place, but I don't know when the mask tracking will be released, or is that data set? I haven't saw it on the web page.
Yes, so we are still actually actively annotating the segmentation tracking dataset. So far we already have 200 sequences annotated, and we are planning to host the following challenges on CodaLab. So for this year's BD100K challenge, we only featured the MOTChallenge. And later we will put all these different tasks, for example, like the object detection, instant segmentation, MOTS, all this on CodaLab. So yeah, so the data is available, but we didn't host the challenge on that data set yet.
So for annotation questions, like there are a lot of nice things in BDD100K. So how could you accurately annotate the mask, especially for the costs very far away? Or yes.
Yeah, that's a very good question. So actually, we labeled the whole data set using like the annotation tools called Scalable we developed in Berkeley. So like one thing when we label the different masks, we have this attribute to each annotated instances. For example, you can specify instances as occluded or like a very crowded scene. And for those, this will be considered as like a very challenging instance during evaluation. We can either choose to filter them out or put the special labels compared to those. So, and for evaluation procedures, we usually have like two annotators to annotate the mask iteratively. And then after you have the raw annotations, we'll do this quality assurance to just verify the annotations. So hopefully that can guarantee the annotation quality.
Okay, so a question relative to BDDK dataset and MOT dataset. As we know, for MOT dataset, maybe the static people or some people being excluded, not considering as a ground truth. So I'm wondering in BDDK, especially for the bicycles, is that some bicycles that are parking maybe on the walk lane or some parking or just parking in other place, not on the road, it's not being considered as a ground truth? Because in the BDDK challenge, although I outperformed the baseline on second place a lot, but my bike recognition is so low. So I have this question.
Yeah, thanks for the suggestion. I think one thing I noticed personally in this data set is the large imbalance through the different categories. So for example, I think one reason I can think of like a back performance is lower is probably because of the number of available training examples on back is also much lower, much smaller compared to other categories like a person or car. So that's one of the challenges in this data sets.
Okay, thanks for your answering.
Yeah.
Yeah, so also from our side, thank you very much for your talk. I think this data set will be a very interesting addition for those tasks and a big help for the community. So one thing I've been wondering is how large is it actually if you download it? How much space would you need to reserve in order to be able to process the entire data set in one go? This must be over 1,000 hours of video, right?
Yeah, so actually when we annotate this data, so each video is about 40 seconds. So the original recording is through iPhone, so which really runs like 30 FPS and then by 720p as a resolution. But during our annotation and the construction of this data set, we actually sample the frames at 5 FPS. And then like annotate only those selected frames rather than the raw videos. We do provide raw videos on our our website. So we have a website for downloading this data. And for those, we do have the raw videos, but for most of the cases, we will just split into different splits and then like have people to download different shares.
Okay. Okay, yeah, but still a monumental task.
Yeah, it is a lot. I mean, like similar to this challenge, we also have a BDD MOTChallenge as part of the autonomous driving workshop, and that one is actually, I think as some of the participants may also be here on the call, and it's actually pretty like time consuming to train such a like model like on our data sets. And that's also one of the motivation. How can we scale up the existing multi-object tracking data set and see what's the new challenge and the new opportunities there? So, and I think another thing observed in our data set and the setting is it's actually pretty, I think it's actually pretty noisy since we did not do a lot of like a manual filtering to our data set. So you can see like, for example, because it's camera, like a cell phone put on the dash, like a dashboard of the drivers. So sometimes you can see the different lighting condition and even some glares from the window. So all those can increase the challenges of the data set. But I do think that's actually reflecting the reality if we want to try to deal with like develop models on real world data sets. So that's one thing I want to mention. And the other part is the data is pretty like, I mean, like the objects, the average objects on the data set is quite large compared to many of the previous data sets. So because, for example, if you drive on highway, especially like in a Bay Area, it could be very crowded, like 1,000 cars appeared in the same image. So that's also a quite challenging thing for most of the MOT models.
Mm-hmm. Yes, very, very much so. And yeah, even running new algorithms on this data set is quite time consuming. So you automatically you will by this design fix the problem that there can't be too much test set augmentation simply because the data set is so large.
Yeah, I think in one of our homogeneous multi-task learning, we found that when people usually do this like similar task structures, and we did similar things, but there's not too many improvements as the data sets scale up. So this is also saying like could potentially provide an opportunity to really evaluate some of the models which were designed for smaller data sets, maybe like data augmentation or like some post-processing like techniques may not be like working perfect anymore. So we will see. I don't know for sure, but I think it could be something interesting to see and study. Yeah.
Mm-hmm. Okay, great. Yeah, so thank you very much again for this presentation.
Mm-hmm. Yeah, thank you.
And
yeah,
I think we can hand back to Paul for the next item on the agenda.
Okay, thanks a lot for the presentation. Maybe if you're still there, one more question. So I'm very happy that you also created another data set with MOTS annotations, and it seems to be quite a bit larger than Kitty MOTS. Did you try or consider using the larger training set of BDD to improve the results on Kitty, or to combine the training sets in some way?
So I think we conducted the domain adaptation study on this one. So potentially you can use like trained models on BDD and try to transfer to other data sets like Kitty, cityscapes. So, but we don't have the benchmark models or baseline models for combining the training data sets together. So that's the part we don't have at now. So what we do have is this like a domain adaptation models across different data sets, as well as different domains created by BD100K. Since the data set is captured in different geolocation, different time of day, potentially you can just create different macro domains within the data set. So we also study those adaptation problems under this data set.
Okay, thanks a lot.
Yeah, thank you.
Okay. So now it's time to continue with the results of track 3. So I'm going to start the screen share again. Okay, so as a reminder, track 3 was with the given detections. And here the methods had to subselect from these detections and to link them over time. And it was not allowed to create additional detections. And here the special thing was also that it was on both data sets together with the same method in order to encourage methods to be generalizable. And here we had 13 submissions. And the total score was a combination of the 3 subscores: cars on Kitty MOTS, pedestrians on Kitty MOTS, and pedestrians on MOTS 20. And for each of them, the SMOTSA score. And the total score of the best method was almost 70. So it seems especially pedestrians on Kitty were hard, maybe because there is not a lot of training data for this. But also here the absolute performance of 70% seems to be relatively high on average. So now I'm excited to hear the presentation from the winners, which will be IA-MOT, instance-aware multi-object tracking with motion consistency. So I hope that Jiahui Sai is here to present.
Yeah, hi, Paul.
Hi, okay, then you can share your screen.
Sure.
Looking forward to your presentation.
Okay, so hello everyone. Thanks for attending our presentation in the BMTT workshop. I'm Yizhou and this is Jiarui, and our team also include Hao Tian, Hongming, Cheng Qian, and Professor Zhengnen Huang. And we are from the Information Processing Lab at the University of Washington. And we would like to introduce our method, IA-MOT. Yeah.
Sorry.
Oh, okay. Okay, so we are going to present our method, IA-MOT, instance-aware multi-object tracking with motion consistency, which is a winner of the track 3. So first of all, I would like to give some background knowledge of this talk. The track 3 in the BMTT is the tracking-only challenge. It aims to track both cars and pedestrians, and with given detections and segmentations. And gap filling or running additional detectors are not allowed. And as for the data set, the track 3 contains the sequences from the both KD MOTS and MOTS 20 with the various resolutions, frame rates, and viewing points. And to evaluate the performance, the SMOTSA is used to measure the detection, segmentation, and as well as the tracking quality. And finally, our proposed IA-MOT got a winner from the 13 teams with the 69.8 as MOTSA. So the pipeline of this talk includes the following sections. Firstly, I will give a brief introduction on our proposed method and then talk about our instance-aware feature extraction from the given detections and as well as the instance segmentation masks. And after that, our teammate Jiarui will discuss about the following online tracking with the short-term retrieval and re-ID with the motion consistency as a post-processing stage. And moreover, our implementation as well as the performance on the KD MOTS and MOTS 20 dataset will also be explained. And finally, we will give a summary. This is an overall framework of our proposed method, IA-MOT. The framework can be basically divided into 2 parts. The first part aims to extract the embedding features from the provided detections. And using these embeddings, the second part mainly do the object tracking to obtain the final tracking results. So first, images are sent into a mask RCN architecture with an extra embedding head to extract the bounding box features for each detection. And second, spatial attention map or SA map for each detection is generated. And then they are applied to the bounding box embedding features to obtain the instance-aware embeddings, or we can say IA embeddings. And after that, these IA embeddings are sent into the tracking stage. A Hungarian algorithm is firstly implemented, collaborating with the short-term retrieval or STR, in short, to associate objects in short term. And then re-ID is also used as a post-processing stage to connect the tracks with long-term occlusions. So let me first talk about how to extract instance-aware embedding features using a mask RCN-based network. So based on the original mask RCN, we add another embedding head to obtain the embedding features for the later tracking stage. And during the training, the 3 heads are jointly trained using this loss function. and it joint considered the bounding box loss, mask loss, and also the embedding loss. And here the embedding loss is calculated on the instance-aware embedding after the spatial attention is applied and trained by the cross-entropy loss. And here during the inference stage, we use the given public detection bounding box as the region proposals and use the given public masks to generate the spatial attention. So the basic idea of the spatial attention is to do a filtering for the background information in the bounding boxes. So the intuition is that to get better embedding features, we want to keep the foreground features and suppress the background features. So during the training, the SA is generated using the mask head output. And during the inference, it is generated by the given public masks. And here are some spatial attention map examples from the both KT MOTS and the MOTS 20 dataset. And we can find that our spatial attention can be focused the original bounding box embeddings to the foreground regions. To illustrate the quality of our instance-aware embeddings, we show some feature visualization here. Using the MOTS 20 sequence 11 as an example, the figures on the left shows the average inter-object feature similarity and intra-object feature similarity with or without the spatial attention. And we can find that it can be separated better with the spatial attention applied. So we can select that 0.8 as the feature similarity threshold. And the right figures are embedding visualization using the TSNE. With the spatial attention in the training stage, we can see that the appearance features are distinctive and well clustered.
Okay, so here I will explain how the detections are associated. Firstly, the given detections and corresponding features in frame T are assigned to the tracks that show up in the last frame by Hungarian algorithm, so which uses the mask IOU and feature similarity as the cost to minimize. And then the match tracks are updated, and tracks that find no matching detections are considered as lost. Unassigned detections and the lost tracks are reconsidered for alignments with looser constraints in the short-term retrieval module, so STR for short. STR match tracks are updated and conduct possible bounding box interpolation. So if not, the new detections will be initialized to new tracks. And also besides, lost tracks are checked periodically to see if they are lost for too long. If there's no record for the previous N1 frames, these tracks will be marked as terminated and no longer valid for the above online tracking. And the cost function here of Hungarian matching include the mask IOU between the detection of a live track in the last frame and current detections, and also the cosine distance of the features. The feature of a track is the stack of the first N and the most recent N frames, so 2N in total. It is also common practice to use the aggregated features. But however, we found that due to the difference in visibility, size, and the surrounding objects, the temporal connection of the embeddings cannot be simply weighted and added up across the frames. Also, averaging over the similarity smooths the correspondence and introduces ambiguity. So we choose the maximum number as the similarity. While the short-term retrieval module handles missing detections, we also introduce the tracklet re-identification as post-processing to deal with occlusions. So first of all, if two tracks do not overlap in the time domain and they are within N2 frames apart, saying T1 and T2 as example. And their features are similar. They are considered as candidates for reconnection. And then the Hilbert regression is used to extrapolate the interval respectively. The average IOU of the extrapolated bounding boxes is confined to be above the threshold. Meanwhile, the motion of each trajectory is defined as the average moving vector of the top left point of the bounding boxes in the last or first n frames. So n equal to 5 for the tracking length if it is shorter than 5 in the implementation. And the cosine distance of motion 1 and motion 2 should also satisfy the criteria. So to remove the false positive in the given detections, including duplicated and objectless detection, we first apply confidence thresholding 0.3 and the minimum bounding box size filtering. In addition, for two overlap masks, if the overlap area is larger than 70% of the smaller mask area, the small mask will be discarded. For example, here, the main mask in red and has code in blue overlap, and on the right, the lady is detected twice. So here, with the given mentioned conditions, smaller masks are dropped. So here, the false positive is reduced. And similarly, after tracking, we also used average bounding box aspect ratio for pedestrian and average confidence and track IOU to remove non-target objects or duplicated tracks. Our proposed method is the winner of 2020 BMTT Challenge Track 3 with 69.8 as MOTS 8, and we are the first in MOTS 20 dataset and also have great performance in the Kitty dataset. Here are two examples in the MOTS 20 dataset. So our tracker handles occlusion well in no matter it is moving or static camera or different object size. And also the tracking is smooth with very few ID switches. These are two demos in the Kitty dataset. The tracking is still continuous in the sense of turning or crowd parking on both street view and highway view. Okay, to summarize, our proposed method consists of three parts. First, the features obtained from a pre-trained mask as CNN with the given detections as region proposals and the mask as spatial attention. And second, Hungarian algorithm and short-term loss track retrieval helps to connect the detections. And third, considering feature similarity, trajectory, and motion consistency jointly, the ReID module further reduced the chances of ID switch. In the end, we would like to thank our IPL group members and advisor, Professor Jianwen Huang at the University of Washington, for their ideas and assistance. So more detailed information will also be released in our lab website. Thank you. We are happy to take any questions.
So thank you very much for your presentation.
Thanks.
There was a question on chat that just came in. Is the weight of mask IOU the same for different data sets and different categories?
Is the weight of so it's the same for both MOTS and KD dataset and for the same categories.
So we have one set of the parameter for the pedestrians and the other for the cars.
Yeah.
There are differences between the cars and pedestrians.
I mean, for the number of frames, we are different. Let me show the slides. So for example, here, the number of frames to determine the termination of a track and one, and also here, the number of frames to do the re-ID are different for car and pedestrian because of the difference of the velocity. For the other ones, like the confidence bounding box size and the overlap ratio, and also average confidence overlapping tracks are the same for both dataset and both categories.
Okay, there is another question.
Yeah. The question is the motion consistency offline? Yes, it is. So, this is our pipeline. Our framework is online with the Hungarian algorithm and short-term retrieval. And the reality is a post-processing part, which use the motion consistency. It's offline.
Okay, thanks for your presentation and congratulations on winning.
Thank you.
I'd also like to ask one question. So what did you find most challenging in this track? And where do you see the most potential for improvement?
Yeah, thank you for the question. So for the most challenging part, we think that is actually it's for two different data sets. We have the pedestrian parts in KD and also in MOTS. So the object size, resolution, and also the frame rate is pretty different. And there's a lot of parameter to tune in the whole framework. So the joint optimization of the two data sets is quite challenging. And also for feature improvements, as you can see, we actually have a detector here. So to utilize a private detector and get high quality mask and detections as the provided ones are probably the future directions for us to explore.
So I guess you have more experience with this. So the provided detections, do you think they were reasonably good, or should we have provided better detections here?
That's actually pretty high quality ones, I think, compared with other MOT benchmarks. And I think probably you can provide some noisy detections. The provided detections are quite perfect. So there's very few false positive or or missing detections. So to get a more robust tracker, I think noisy detections may be more useful.
Okay, I see. Yeah, so our reasoning actually was we have these good detectors, so let's use them and then see what tracking can do with these detections. So I found it a bit weird to artificially introduce bad detectors here.
Okay, so I see there's another question here. The question is, would you please introduce more about the attention map, how to train it, and how do you use it? I will go back to the slides.
Yeah, so for the spatial attention here, the spatial attention is mainly, I just mentioned, is mainly to filter out the background in the bounding box region. So so here during the training, we use the information provided for the intermediate result from the mask head to send into a to generate the spatial attention map, and apply this spatial attention to the embedding head, the output of the embedding head. So the embedding loss is calculated based on the instance aware embeddings instead of the bounding box embeddings. So this during the training, we have already considered the spatial attentions during the training the embedding head. And during the inference, we just directly take the public masks to use the public masks to generate the corresponding spatial attention and apply to the extracted embedding head, and to get our instance aware embeddings to send into the following tracking stage.
Okay, so thanks again.
Thank you. Thank you.
So the next session will be spotlights. So in total, 4 spotlights have been submitted. Actually, we hope for a few more, but yeah, now I'm gonna play the 4 spotlights which were submitted. So I'm not sure for which of them the people who recorded them are in the Zoom meeting. So afterwards you can ask questions, but we need to see who's actually here to listen to it. Okay. So I'm just going to play all the 4 spotlights now.
Hello everyone, my name is Jimmy Lee. I'm a master degree student of Gaemyeong University in South Korea. In this presentation, I'm going to briefly introduce my research paper. The title is Best Multiple Object Tracking Using Sham Random Forest Without Online Tracker Updating. This figure is overall structure of our system. To build an efficient framework in terms of MOT performance and tracking speed, we propose a sham random forest that combines an accurate random forest. First, during detection processing, we extract partial feature map from first and second layer of darknet 53. Next, 2 feature vectors are generated by applying global average pooling layer to each partial feature map. And these are concatenated to become one final condensed appearance feature, which contain distance information of each input. Then finally, we generate score metrics using sham random forest for data association processing. For training, we adopt n-fold cross-validation to improve the accuracy of random forest. And during the learning process, the shared rule-based random forest is learning the direction of increasing similarity to the first pair and direction of increasing difference to the second pair. When the learning is completed for all k-folds, the random forest with smallest total cost is determined as a final random forest. We compared our method with other state-of-art online MOT methods. This figure of comparative experiments shows that sham random forest is relatively faster than other MOT algorithms with similar MOTA. In this paper, we proposed sham random forest which can be quickly learned and tested with a small number of parameters. According to the nature of random forest, the proposed sham random forest uses k-fold validation instead of the backpropagation, and thus the learning is fast and optimal tree rules can be properly generated. In addition, because of the rule of tree constituting the random forests are shared with each other, the memory requirements can be reduced during the entire multi-object tracking processing. Thanks for your watching, and if you want to ask questions, feel free to ask through my email.
We present our framework for real-time 3D multi-object tracking and segmentation powered by sensor fusion. Multi-object tracking is an important task for reliable. We present our framework for real-time 3D multi-object tracking and segmentation powered by sensor fusion. Multi-object tracking is an important task for reliable motion planning and navigation for mobile robots, for example, self-driving cars. Existing methods either detect objects directly in 3D using sensors like LiDAR, which have a high accuracy but are sensitive to occlusions, or using a combination of 2D images and depth estimates, which allows.
Okay, for some reason the video for this one didn't work, so maybe let's first skip to the next one and I will try it again.
Hello everyone, this is Haotian Zhang from the University of Washington. We are delighted to present our paper, LIFT's LiDAR and Monocular Image Fusion for Multi-Object Tracking and Segmentation. Here is the framework of the proposed LIFT algorithm, which consists of a three-stage pipeline. First, a 3D object detection is performed on a LiDAR point cloud to get accurate object 3D bounding boxes, which enable us to do a more robust 3D tracking. Then, the projection of these 3D bounding boxes are used as a pre-computed proposals to cascade mask RCNN, not only to generate a segmentation mask, but also can help us to merge the small objects that are not previously detected in 3D. This is able to bridge the 3D workspace and 2D image space consistently and produces a high-quality mask for each instance. Finally, we also consider employing the optical flow as a source of additional information to further guide the pixel-level segmentation. For some tracklists that are not well aligned, a re-ID approach is also adopted to reconnect those tracklists. Given the LiDAR point cloud, a 3D part aware and aggregation network is adopted to get accurate 3D object locations. The projected box onto the 2D image is sent into the FaceNet to get appearance embedding. Then a graph-based tracklink net tracker, which takes both CNN appearance and object spatial information, is then applied to robustly associate corresponding detected objects along time. Later in the second stage, we project each frame of the 3D trajectories onto 2D image and treat them as the pre-computed region proposals for a cascade mask RCNN-based network with point rent head to generate the mask results. Nonetheless, for those objects that are not detected by the 3D detector from LiDAR point cloud, but detected by the 2D object detector from images, we use Hungarian algorithm to merge these detections with existing trajectories. We further improve the mask quality of the tracked objects in videos by using the temporal information, where the segmentation mask can be further refined from the previous frame's rough estimate. We also employ the optical flow as a source of additional information to guide the segmentation. In parallel to the above framework, we proceed to compute a second output mask using the magnitude of the optical flow field as the input image. We then fuse by averaging the two network results and generate the final output masks. A re-identification approach is also adopted to reconnect tracklists due to occlusions or fast motions. We use the trajectory level of features in the tracking refinement process. Overall, we ranked the second place among 16 teams in the CVPR 2020 workshop, the track 2 of the BMTT challenge, KKD and MOTS. Here are the qualitative performance and some video results. Thank you for watching. Please refer to our paper for more details.
Hello everyone, we are the team of MCFPA approach. So MCF is a traditional but very useful method. We follow the traditional formulation of multiple object tracking as the mean cost flow optimization problem. Given a video with multiple targets, our goal is to track k moving targets in the detector and track manner. The inputs contain a set of candidate object detections provided by detectors. A measure of correspondence between detections are required. The tracking problem is thus formulated as a joint optimization problem of simultaneously selecting detections and connections between targets, which can be modeled by a MAP estimation objective. The MAP optimization can be cast with specific constraints encoding the network structure of the tracks. So there are three models inside the MCF. The first model is an LR model for rescoring box, represents the observation edges in MCF. And the second one is a GBDT model for affinity score, represents the transition edges. The GBDT model entails several informations. As for the appearance feature, there's a reality model. We fine-tune the MOT and KT pedestrian data for our person reality model. As for the KT car reality model, we didn't fine-tune, so we got a worse result on KT car leaderboard. There are several shortcomings of MCF. So the first one is it's a time-consuming optimization approach. So there are also batch computing implementation of MCF, so it's also a suboptimal result. And the second one is the affinity score often generates for box level, so they will produce much more FPs or break the trajectory when occlusion happens. So we come up with a simple but effective method called the trajectory fix, and this is our PA module in our approach. We can do several operations inside this module. First one is refine trajectory. We borrow some ideas from the approach called SQE. We can just use the similar idea to judge whether or not there is a FP happens inside a trajectory. And the second one is we can relink broken trajectories. By analyzing the appearance of trajectories, we can relink similar ones. We use the second one to implement in our MCF approach because we can set a more aggressive parameter to determine whether or not to do a box level link. We don't need to care much more about FPs in MCF. Inside the PA module, we use a state-of-art SOT model with a discriminative score for relink. The model needs to be robust with occlusions or auto views and similar scenarios. So we use the tracker of SPM, the nearest and the state-of-art method. We got good results on the 3 tracks, especially about on the data association scores of MOT. For example, the IDF1, ID switch, and frag. We rank good results in all 3 tracks. Thank you. That's our approach. We are from Alibaba Group.
We present our framework. We present our framework for real-time 3D multi-object tracking and segmentation.
One moment. So one of the videos didn't work correctly, but there is a YouTube version which I'll now try to play.
We present our framework for real-time 3D multi-object tracking and segmentation powered by sensor fusion. Multi-object tracking is an important task for reliable motion planning and navigation for mobile robots, for example, self-driving cars. Existing methods either detect objects directly in 3D using sensors like LiDAR, which have a high accuracy but are sensitive to occlusions, or using a combination of 2D images and depth estimates, which allows detections of heavily occluded objects but at lower accuracy. In our work, to combine the strengths of these two approaches, we propose an online tracking framework that eagerly integrates all available object observations from both sensor modalities to obtain a well-informed interpretation of the scene dynamics. For each frame, the sets of 3D and 2D object detections are fused together to form object instances using only their overlap to drive bipartite graph matching. Next, these instances are associated with existing tracks using 3D overlap between observed and predicted 3D locations. Instances and tracks that did not find their match enter the second association stage, this time based on 2D overlap. Matched instances from both stages update their track states, while unmatched instances start new tracks. In the end, a simple set of conditions is applied to discard all tracks and report information about the confirmed ones. Our method achieves state-of-the-art results for multi-object tracking segmentation and both 3D and 2D multi-object tracking while running in real time at 90 frames per second on a commodity CPU, almost 20 times faster than state-of-the-art MOTS methods. It requires no tracking-specific information and generalizes to different input detection sources, which means it can be directly applied to your selected sets of 3D and 2D detections. For further improvement, it can also support other dissociation cues, for example an appearance-based model. Our code will soon be available online and we invite you to check out our short paper for more details.
Okay, so I'm a bit sorry for the technical difficulties. I think the quality just now was not really great playing it from YouTube, but at least we still got it working. So these were the spotlights. So if I'm not sure which of the speakers are actually here. So in case the speaker of some spotlight is here, we could ask some questions. And okay, it seems there are no questions for the spotlight speakers. So the next session will now again be an interactive session with a discussion. So I would suggest that we make another 3-minute break and afterwards continue here. See you soon. Okay. So this will be the second interactive session with some discussion. So let's see how much there is still to discuss after the first session. So I guess if anyone has more comments about the data sets, the evaluation measures, or some new insights from this workshop, or what you would like to be improved in the future, would now be an interesting time to talk about this.
All right, let's talk.
Okay.
So I do have a comment on like the tracking field in general, because it seems to me that the tracking performance, the MOT-A, MOT-P, usually depend a lot on the detection quality. So essentially, the best detector wins, a lot of these challenges. And I know there is the category where you use the provided detections, but then people can still cheat in some sense, that you kind of propagate some methods. For example, actually one of Laura's work on the tracking without bells and whistles. So essentially you are propagating detections from past frames to the current frames. So essentially you have more frames, more detections to work with, and that gives you a better recall. So what I'm wondering is, how can we make sure that this is essentially still a tracking challenge, it's not a detection challenge or a segmentation challenge?
Okay, very good point. So yeah, we had the third track where the detections were given, and you said it could still happen that some people cheat.
Right. For example, you have multiple detections per frame, right? So technically, you can design an algorithm where you say, okay, this is the tracking without bells and whistles paper. Essentially, you can say I propagate some of the detections from my past frames to my current frames. Then you suddenly have more detections per frame. And
exactly. So here we had a special rule to limit this a bit. So the output of the tracking method was only a mapping from from detection IDs to track IDs. So the methods could only subselect from the detections and link them into tracks. So there is no way to create new detections. So at least this would limit this a bit.
I see. Yeah.
But you're right, it's evaluation.
Output space. You can.
Yeah, the output space was very limited.
Like in a feature representation, you can still do whatever you want. But in the output space, you cannot generate new tracks.
Exactly.
That makes sense.
And also, I think you're right that MOTSA or SMOTSA evaluation measures are very strongly based on the detection performance. And we were also not very happy with this. So we did this now for consistency with previous challenges and evaluation measures. But Bastian already mentioned in the first discussion session that we are actively working on other evaluation measures which focus more on the actual tracking part. So one thing we also did is to evaluate IDF1 for MOTS 20, but we did not use this here to determine the winner, but it was still interesting to also look at this. And yeah, I fully agree that this is so much based on detection, and in the future we need to somehow disambiguate a bit better between the detection and the tracking performance.
Okay, yeah, that sounds great. Oh, there's another question.
In the chat. Okay. All right. So Fan Yang said, I found some teams can use 3D LiDAR data on Kitty. How to find the relationship from MOTS files to Kitty LiDAR files? Could you add instruction to the data introduction? Okay, so I have to say I also don't know the details here. So the Kitty MOTS dataset uses exactly the same sequences as Kitty tracking. And for Kitty tracking, there was LiDAR provided, I guess. I'm not sure if the mapping is straightforward or something needs to be done there. Okay, there was another comment. So it seems like you can just download it for the 2D Kitty tracking benchmark and then use it. But also to make it more fairer, for the third track, we disallowed this because we wanted just to have tracking competition without 3D. Okay. Are there any other questions or comments? Okay. Sung Chun Lee asked if there is a development kit for MOTChallenge in MATLAB or Python code. So for the new challenges here, we provided Python code. We are not doing anything in MATLAB anymore. I think for the older MOT challenges, there might be only or also MATLAB code. So we have a repository called MOTS I will write the link into the chat, which are Python tools for the current challenge here, for visualization, evaluation, and data loading. Okay. Anything else? Otherwise, I think we can soon move to the final invited talk, although we're a bit ahead of schedule now. Maybe
yes,
one more question.
We are a bit ahead of schedule, but I think since this is the last item for the workshop, I think it will be fine.
Okay, then let's do it. So I think you wanted to introduce the speaker, Bastian.
Yes, let's quickly verify. Alyosha, are you already there?
Yes.
Yeah, in fact, he's already screen sharing.
Yes, very good.
And the screen share works.
Great. So let me quickly introduce you. So it's our pleasure to welcome Alyosha Efros from UC Berkeley for this final talk of the workshop. Alyosha received his bachelor degree in computer science from the University of Utah in '97, and then the PhD in a PhD degree from UC Berkeley in 2003. He afterwards did a postdoc stay at Oxford University, and he was in the faculty of Carnegie Mellon University for 9 years, but also being affiliated with ENS, École Normale Supérieure, and INRIA in France, before then finally going back to UC Berkeley, but this time as faculty. Alyosha is a great aficionado of mountain hikes, art history, and Paris architecture. And he has been a prominent figure in computer vision for a very long time, highly valued in our community for his ability to think outside the box and to come up with interesting new ideas. And it's also therefore that we're very happy to have gained you as a speaker for this workshop. And we're curious to hear about your thoughts here on visual correspondence and tracking.
All right. Thank you so much for inviting me, and I am very sorry that we can't, grab some beer and sushi in Seattle after this. But I guess we'll have to wait until next year. So I'm going to give you a outsider's view of this these topics. So do forgive me, since it's been I have one paper on video when I was a grad student more than 15 years ago, and I have just restarted looking at the video again. And so, you know, I want to even like ask, why video? You know, why is video good, right? Why not just take a bunch of still images, right? And so if we step back and think about it, well, there are a few reasons. One reason is just more information, more signal, right? So we look at, you know, look at the still image, and, you know, sometimes you think, okay, this might be a person, but it also might be like a splotch of paint on some canvas. And indeed, for the left one, it is a splotch of paint on canvas by Jackson Pollock. But as soon as you turn on the video, it becomes very evident that this is, you know, the one on the right is a person, right? So there is a lot of information that is captured in the motion, and we want to get access to it. A second, maybe for me at least, even more important reason is that this is a way to capture, to learn about correspondence. Okay, so here I'd like to quote one of my favorite writers, Jorge Luis Borges. In one of his stories, he says, "It irritated him that a dog at 3:14 in the afternoon seen in profile should be indicated by the same noun as dog at 3:15 seen frontally." Okay, so the fact that this is the same dog, it's not at all obvious until you realize that the world is continuous. And how do you realize it? You realize it because of video. Video gives you this super important continuity signal to learn about the world being continuous. We know it's very important because of some beautiful work by Wood and colleagues. So he has these little VR farm for chicks. So a chick is born in a little VR cage, and so everything the chick sees is being projected and being fed to it by the researchers. And so what they can do, they can do various experiments. So one of the experiments they did is that they showed the chicks videos which were not visually contiguous, something like this, right? Where things were not physically plausible. And it turned out that chicks raised with videos like this were unable to function visually compared to chicks that saw things that were in a control group where the videos were temporally smooth. And so this tells us that continuity is absolutely crucial for visual development, not just in humans, but even in lower animals. Finally, one could also argue that, you know, video is good for ordering, keep putting things in order. You know, they say time is what keeps everything from happening at once, right? And so time is a way to lay things out in, or video is a way to lay things out in time and kind of give steps. Here, I'm not actually sure I agree, because here is an instruction for folding a paper airplane, and you know, it's not a video, it's just a bunch of stills, and that's basically fine. That's enough for us to know what's going on. So I think for this, you don't really need video, you don't really need continuity. So a little set of discrete samples might be enough. So we're not going to talk about this, okay? We're going to talk about the other two. So because I'm kind of an outsider, and because, you know, I'm an old fogey, I want to give a little bit of a kind of a perspective from the olden days of video, especially for the young folks who might not have seen this. In the olden days, life was very nice and clean. We had this beautiful story of a spatial temporal volumes, right? So basically we had these XYT spatial temporal volumes where we had the time was just another dimension, right? Instead of a 2D image, you had a 3D cube, right? But then everything else just worked out. And there are these beautiful, old papers. For example, Ted Adelson had a paper. He noticed that if you chop a video at the legs, then you get these beautiful braided patterns when people walked. Okay, and so he had a paper on detecting these braided patterns and then tracking people that way. It's really, really beautiful stuff. There is a series of papers on looking at spatial temporal texture. One of the work by Leahy and Michal has really inspired me when it first came out, on basically looking at spatial temporal gradients in that XYT volume, and just doing histograms of them and using that kind of an early learning approach, using that to tell apart different actions. And it worked surprisingly well. So, and frankly, I think even now, the whole area of action recognition, it's basically doing texture recognition in the spatial temporal volumes. And no wonder that these things are coming back in the guise of 3D convolutions, and they're doing quite well in action recognition. Segmentation was another thing that was big in late 90s, and one could work like normalized cuts by Shi and Malik would be basically a way to make connections, to construct affinities between pixels both in space and time, and then throw it into some spectral clustering approach, and then get these spatial temporal volumes out of this, and do segmentation this way. One paper that I just wanted to spend a little bit of time on, just because I love it so much, and that I noticed that the young kids don't know it anymore, and it's a shame because it's just such a beautiful paper, called video textures. So the goal is to given a video clip to basically make it run forever. Basically to have it as a texture, okay? And the idea goes back all the way to Claude Shannon and his theory of information. He mentions a way to generate English sounding text by using n-grams. So you assume that English has a Markovian model, and then you use a large corpus of text, train your distribution of n-grams, and then you just sample from this Markov chain, and you can do it on letters, or you can even do it on words. So for example, you can say, start like with a bigram, we need, and then say, okay, what's the next likely word after we need? Well, maybe to, need to. Then you shift your context, say need to what? Well, some verb, right? Need to eat. Then shift it again to eat what? Well, probably cake, right? And you all know this because this is exactly what your SMS on your phone does. It basically uses the Shannon trick for this. And I was very inspired by this, so we did a texture synthesis approach, which is basically doing a Markov chain on pixels. So this is like pixel CNN 20 years early. But I think what was even more impressive was the video textures folks who said, well, you know what, we can do Markov chains on frames. Let's just make a video, turn a video into a random walk on this Markov chain, okay, and make this way, make it run forever. And what the way they did it is they created an affinity matrix, all frames to all frames, very simple. I think they do L2 distance between frames, and then they basically started looking for good correspondences or good transitions. And the idea here is very simple. It basically says, well, if you're in a video I, you can go to the next frame I+1, but you can also jump if you can find a J from somewhere else that looks very similar to I+1. Because then if you jump from I to J, nobody's going to notice because J is just like I+1. Okay, that's basically the whole idea. And it worked very well. Now, if you just do it for a single frame, it does okay, but it doesn't really preserve preserve dynamics, but then you can just do temporal smoothing, and then you do multiple frames instead of one, and then it works fine. Okay. And what I liked a lot is that you could also do a conditional version of this. If you have some labels on your data, for example, you know how fast this guy is running, then you can actually have a controllable synthesis where you can control how fast your video texture is going to run. And they even had this wonderful experiment where they rented a fishbowl with a fish from Petco for a day. Background subtracted, detected where the fish was headed, and then basically just added this control term, which basically made the fish go towards the mouse, and you get something like this. And this is year 2000. Okay, this is for those of you who have seen some of these GAN video synthesis works. Like, we are really far from this. Okay, this is still way more impressive than whatever we can do right now. Okay, so XYT volumes were very cool for a bunch of reasons, but they kind of they had their problems, right? One main problem is, of course, time cannot be just treated just like another dimension, right? Because of the sampling in T is just much more sparse than in X and Y. And so you can't really talk about real spatial temporal gradients because the T samples are just not very good. And it's also, it assumes an implicit correspondence, right? It assumes that either you have a fixed camera or it assumes some sort of a simple model of motion. And if in the real world, of course, these things are not simple, and these things are very hard to find. And this is exactly where kind of the whole kind of explicit goal of finding correspondences comes in, right? And both optical flow and object tracking are examples of trying to get at these explicit correspondences, right? In optical flow, you get a dense correspondence, a whole flow field, but unfortunately, it's very short range, right? Usually just a couple of frames, and it's not compositable, right? If you keep compositing optical flow fields, that they go crazy very quickly, and it's also quite local around the pixel. Object tracking, it's basically a way to turn something uncooperative into a spatial temporal volume, right? Nice stabilized thing. It's longer range, it's mid-level, but it's one object at a time, and it's of course not very stable. For those of you who are young, you maybe don't remember. I'm sure Bastian and I still remember in the late 90s, all these tracking papers were their metrics that they reported was time to failure. How many frames do you track until it fails, right? And it's always like under 100 frames, so like under 2 seconds or 3 seconds, right? And that's really what kind of the context of the currently super popular idea of tracking by detection. And this is, of course, the seminal paper, Strike a Pose. I was actually there when David was in Oxford working with AZ and David Forsyth. And this is just, this is really where kind of learning starts to come in. And in a sense, it's also kind of an early example of test time training, where you train on one frame where you can, when you can easily detect a particular person, and then you basically try to find that person in other frames of that video, right? And it's not a it's a natural thing to do, and the results were just way better than anything we have seen before. So everybody was super excited. Of course, now you guys know much better than I. Lots of stuff on this, and now we're using off-the-shelf detector, et cetera, et cetera, et cetera. And then of course, and the correspondence is now kind of more implicit again because it's kind of based on the detector. And of course, you guys are kind of know this much better than I, but all this data association story where you start with these detected objects and then you try to make explicit correspondences in a proper theoretical way, kind of connect them together across video. And I think this is exactly the right direction, but I guess the problem that I see here is at first you still need the supervision, right? You need to get those detectors, and then if you want to track something that you haven't seen before, you don't have a detector for that, it doesn't work. And second is kind of you have this two-step thing, so the data association is kind of a somewhat divorced from the pixels. And so what we wanted to do is we want to see if there's a way we can push towards having no supervision and also kind of starting from pixels. And one of the things that we have been doing in my lab is trying to use self-supervision, and kind of time is a very nice type of supervisory signal, right? It's always there, it's totally free. All you need to do is you need to wait a little bit and you'll get your supervision. And people have been looking at self-supervision with time for a while now. The kind of the more obvious thing to do, especially for learning features, right? The most obvious thing to do is to just try to predict, what's going to happen next. That's the obvious kind of prediction task. Unfortunately, it's very, very hard. It's too hard to actually get anything good right now. What works better is if you do prediction tasks that are somewhat easier. For example, the arrow of time, or unscramble frames and put them in temporal order, or use audio and video signal and see if you can detect a misalignment between them. Or what we were very influenced by, predicting something like color in a future time. And the goal is, of course, to learn a visual representation. So you can always do it more directly. You can just say, okay, let's just take a tracking or optical flow, get some tracklets, and then use the different points in the tracks in a kind of similarity learning framework to learn that all of these patches within the track should be close to each other in our new feature, right? The problem here, of course, is now we are relying on this off-the-shelf trackers or optical flows, and so we will never be better than those initial things. So what we wanted to do is we wanted to somehow get out of this kind of chicken and egg problem. Like similarity requires tracking, but tracking requires similarity. Let's try to jointly learn both. And so what we did last year with the joint work with Xiaolong Wang and my student Alan Jabri is we thought, okay, let's try to use cycle consistency in time, basically forward-backward consistency in the old tracking nomenclature, use that as supervisory signal. Okay, so the idea is very, very simple. So what we're going to do is we have a big deep tracker, and we are going to track in a video, okay, using initially some random feature, okay, and then we don't have any supervision to know if the track was good or not. So what we're going to do is we're going to go backwards. You're going to track backwards until we get to the frame we started from, and now we can compare where we started from and where we ended it. And of course, if we want to be consistent, it should be the same place. Okay, that's kind of your old style forward backward consistency. But now the cool thing is that if we are not there, and of course, you're not going to be there in the beginning because it's a hard problem, well, now you have supervisory signal. You have this delta that you can use as supervision to backpropagate all the way to get your tracker to be better, which will force the feature to be better, and then you do it over and over again. And here is an example of kind of starting from the initialization, and basically as you're optimizing, that the loss is less, the tracker gets better, and so that the feature representation gets better, and you get more and more consistent, more and more cycle consistent. Okay. Now that paper last year, we were very excited about it, but it definitely was just the first step because, well, first, only one patch at a time, so it was slow. Also, the tracking was hard. It's basically winner-take-all tracking. There was no way to kind of consider different hypotheses. And the tracker was kind of complex. There was a whole spatial transformer in there, which is kind of ugly to deal with. And it didn't really improve for longer cycles. I was kind of hoping that we could go really long, but then after about 6 frames, we didn't see any improvement. Worse, for me as a data-driven guy, it did not improve when we gave it more data to train. Because the nice thing about unsupervised or self-supervised learning is that you can have unlimited data, right? You don't need a data set. You can just keep training on more and more data. But it stopped improving. In fact, it even dipped a little bit after more data. Okay, so this year we just finished a fresh new paper that I'm very excited to show you. And this is joint work with my student Alan Jabri and Andre Owens, who is now a professor in Michigan. And hopefully it will be on archive next week. Okay. And it's called Space-Time Correspondence as a Contrastive Random Walk. Okay. So the aim is to learn a visual similarity representation for correspondence from unlabeled video. So the same as the previous work, but we want to focus on simplicity and scalability. Okay. And so the idea is as follows. So again, if we have supervision, how do we learn that this and that patch should be close together? How do we learn their correspondence? Well, we could just basically supervise it with some sort of like a similarity loss or contrastive loss, whatever, right? We could also say, well, we could actually go through all the look at the image in the middle between those two and see where that would fit. And so we can look at the paths through the middle with the middle image that end up at where we want to get to. Okay. And then we can kind of incorporate that in our similarity learning. And we can do it for more frames. But of course, if we don't have the supervision, we can do a similar kind of a cycle consistency trick. We can make a palindrome. So we can flip the video and we can basically make it end where it started. Okay. And so now we know the supervision. The supervision is you need to end up where you started, right? So we can unwrap this cycle into a palindrome. And now we can make this same story, but now it's self-supervised because we don't need any labels anymore. Okay. So the story is going to be, we're going to do a contrastive random walk on the graph produced from a palindrome video. So we take a video, we represent patches as nodes, and then we are basically going to have a random walk. We're going to have a random walk on this graph, and the random walk is going to be guided by the target. We want to hit the target, which is basically the place where we started. Okay. And so we're going to guide this random walk to learn a feature similarity that would get us to the place we started with. But we can do it for the entire video at once, for the entire frame at once, not one patch at a time. Okay. And so now let's look at actually, what the means. So, okay, so first we go from pixels to nodes, and it's pretty sparse. Actually, it's about 7x7 representation. And now it's basically, think about it as like one step at a Markov chain, right? This is basically a transition matrix from frame QT to frame QT plus 1, and it's basically just a dot product between the representations represent this transition matrix. And once you have it for one step, you just multiply those matrices together. This is kind of a standard Markov chain story, right? You can chain them together to get yourself a random walk on our video. Okay. And so again, if now we need to guide this random walk. So again, if we had our target, if we had a supervision, then we can treat that as a positive, all the other places as negatives. And then this is basically a contrastive learning story is very suitable to this. We can just basically upweight the positive and downweight the negatives, okay? The cool thing is that then we can now chain it. So we can have a contrastive problem at every frame, but the label only needs to be at the last frame because they're all chainable. Okay, and so now it's all very nice. And so basically, one label here kind of gives one target gives labels for a whole chain of correspondences down the line. Okay, and of course, if the correspondence is obvious, then it's basically just kind of a unimodal thing. But the cool thing is that even if there is ambiguity somewhere along the way, that ambiguity gets integrated out. So it basically takes care of multiple hypotheses kind of on its own. Okay, so it can deal with multiple paths. And as I said before, this needs supervision. But if we turn this graph into a palindrome, then we turn a supervised problem into a self-supervised problem, and basically we train on that. So this is kind of like, you can think of it as a contrastive learning where the correspondences are later instead of being explicit. Okay, and the code is very, very simple. It's very, very trivial, and it does surprisingly well. So we kind of evaluated it on a standard set of tasks that people evaluate these learned feature representations from video with a standard kind of a label propagation tasks, and we do extremely well. So this is label propagation. You basically, you have your 0th frame, and also usually people have a little bit of context, and we are kind of following that framework to do the evaluation. And so we can do it on semantic part representation. And so here is some examples of that. Here's another one. The sampling, the temporal sampling is very coarse, so that's why it goes so fast. We can do post tracking. So oops, the left one is previous state of the art, and you can see that we are doing a better job tracking. Here is another example. Okay, we're doing better. Okay, I'm going to skip all of those. And we can also kind of cut some edges by doing like dropout, and basically make it more about like a segmentation tracking representation. So basically kind of use the idea of common fate from Gestalt psychology to basically connect together sites, nodes that like they move together, right? Kind of make it more kind of closer to something like normalized cuts on this segmentation approaches. And when we do that, then we increase performance on the segmentation propagation task like Davis. So here is some examples of the Davis example. So this is the prior state of the art, and you can see that there is a bunch of problems, but our thing, it's able to deal with occlusions and it, deals with it much better. Okay. Here is another example from Davis, and this is UVC, and this is us. Some more. This is prior work, and this is us, and we can see that we're not perfect. We lose this guy in the end a little bit, but we're definitely better than before. Okay. Okay, one more. I will. You can see that we're able to deal with things better. Quantitatively, we are state of the art currently. on these kind of metrics. So we're basically beating our old paper from last year by an embarrassingly large margin, but we're also beating the follow-up papers as well, even though some of them actually use twice the feature resolutions, which you would think that should be better. And we are also beating kind of the standard, pre-trained networks as well. And the same for other tasks. And finally, I wanted to kind of show a cute little example where we can do it in a kind of an offline regime where we pre-train and then we run out a new video. But because we don't have labels, we don't have to do that. We can actually self-supervise at test time. Okay. So-called test time training, following the work of my student Yusan, that's going to be an ICML this year. Basically, we can train on the testing video, and this is totally fair because basically we're fine-tuning our representation as we're doing it, and we get some improvement. Okay, especially at on the J recall index. And the nice thing is that we are actually getting benefit from longer paths, so we can go as far as 20 frames, and we're still getting benefit. And very happily for me, as we get more data, we keep doing better. So that's kind of a good sign. Okay, so in conclusion, we proposed a simple and hopefully effective formulation for learning correspondence in a scalable way from completely unlabeled video. And it seems to be very simple, but still outperform other self-supervised methods. And hopefully it can also lead to some kind of more other things that you can do with this idea of a contrastive random walk that I think could be useful for other methods as well. So thank you very much, and I'm happy to answer questions.
Okay, thanks a lot for the nice presentation. So, are there any questions? So I saw one question was asked in the chat. The Zoom chat. So it was from Fan Yang, related to the track self-supervised learning. It really works for single object tracking, but he has not made it work for multiple object tracking. So is there a way to also apply it on multi-object tracking when objects have similar appearance and occlusion frequently happens? And he also corrected it slightly. So he said, sorry, I mean when all objects should be tracked, objects go in and objects go out. Not the case that several objects are tracked, especially when objects are small and crowded in MOTChallenge. How would this work? Okay, I hope this was not too confusing now.
Well, okay. I think, well, one thing is that we're not proposing a tracking method. What we are after here is learning a similarity feature, a representation. So the hope is that this kind of feature you can then put in whatever tracking method you want, and it will hopefully do better than whatever standard things that you're using, right? So we did show examples of these kind of label propagation on things like Davis, which you could think of as tracking, but it's kind of it's kind of a very poor man's version of tracking, right? So it's really just kind of a nearest neighbor kind of thing, right? And that's for better or worse, that's kind of the standard that people are comparing with in this little mini community of self-supervised feature learning. But no, we are, and we should be good at, especially if we're doing this test time training, we should be good at occlusions, okay? Because you can just kind of jump over occlusions and deal with that. We probably wouldn't be that good at things like if you have two things that are very similar to each other, or if you have things that like cross over, because again, this is the feature that we're learning is just like a 2D feature. Like the feature is between two appearances, right? So it's not meant to kind of do this kind of a long-term thing. But the hope is that for some, for those of you guys who are doing work in this area, that using our feature, we hope would be better for you than using some off-the-shelf feature. That's the hope. And we are going to, we're going to hopefully release everything, including the features, online soon. And so then you can just plug in and try it and see if it does work for you better.
Okay.
So, Alyosha, another question. So, first of all, thank you very much for your very interesting presentation. I very much like this idea of self-supervised training, and it has a huge appeal. So, so the prospect, we could just take our computer, put it in front of the television set, yeah, and it would watch TV and learn while doing that. But we have some prior knowledge also from humans. If we do that to humans, they actually do not become smarter at some point anymore. They become more dumb. So, and
well,
and, the reason is that at some point also in the self-supervised learning, since you don't control what you want to learn, you might get processes that reduce the variability of your feature matching, and you tend to get overfitting. What are your thoughts on that one?
Yeah, no, I agree. I think the evidence is a little bit mixed. It's true that there is some, of course, it's much better to be active. It's much better to control the changes in your environment rather to just be a couch potato and just watch TV all the time. On the other hand, we do know that, for example, quadriplegic people, quadriplegic children still learn to see, right? They're not blind, even though they are not able to affect their physical world. So they are indeed couch potatoes in terms of, in that sense. But they are able to learn enough in this passive way. I don't know, maybe it takes longer for them, or maybe they're not as good, but we know that they do learn it. And the kind of the classic experiment with the two kittens, the held and held paper, I think results from this paper has been a little bit overemphasized. If you actually read the paper itself and you read some follow-ups, the differences between the active kitten and the passive kitten were actually very, very small. So definitely active exploration and active learning is definitely going to be better, cheaper, faster. But then you have to get yourself a robot, and then it kind of has all these other issues. Passive learning probably has its place. Passive learning is probably something that does happen. It's not it's definitely not the only thing that happens, and it's maybe not even the primary thing that happens. But we are now trying to learn some, the basics, right? And then hopefully then you can fine tune with more active exploration, because again, actively you're not going to actively see everything, right? So there needs to be some sort of a pre-trained thing that is already kind of good enough, before, again, with babies, right? The babies are able to see. The first year they're not really moving anywhere, but they're still able to see. The visual system develops. So I think, yeah, I think active is good, but passive is probably also has its place.
I actually think it's you bring up a very, very interesting point, active versus passive. But I think the issue is a bit deeper here. So if you just have passive learning, then at some point you will not see enough interesting new stuff anymore. Basically everything that you have seen already, that is already known. Active if you do active learning, you have the chance to manipulate the world in interesting ways to see something new. And then when you have this passive way, you still occasionally do see something new. So you have the chance to improve your learning, but 80% or 90% of the time, the changes that you see will not be really thing that improves your understanding of the world. So you have more chances of degrading actually your learned representation. So do you think you need to build in some controls to stop this degrading?
I don't know. I don't think we have any. I don't think we tried. Like, what I want to do is I want to really run a computer system on all movies from Hollywood, every single one. Or I want to hook it up to, you know, National Geographic's TV channel or BBC, and just make it watch all the programs all the time. Nobody has tried this. I think that there's plenty to learn. Maybe maybe like after a couple of years, it'll be like, oh my God, this is all the same. But 2 years of data is way more than anyone has ever tried.
Mm-hmm.
So I'm optimistic. And in fact, that's what I'm trying to get my students convinced to do exactly that. It's a little bit hard, but yeah. But I do believe that it might not work, absolutely, but I don't think we gave it a fair shot.
Mm-hmm. It sounds like a very interesting endeavor. Yeah,
in a couple of years, I'll let you know what we learned from. Yeah.
Okay, are there any more questions from the audience?
Sorry, I had just a clarification question. Yeah, great talk, Alyosha. Just in the last work on the the follow-up of the cycle consistency loss, what I didn't understand is what forces the feature to move away from their original positions, because they could just cheat. Every pixel can just say, okay, I'll just stay put. And then after the palindrome, they have no loss because they see themselves.
Right. So we're doing the same thing that we did in the previous work. They actually don't know their XY coordinate. We don't the nodes are just nodes in a graph. So they lost their XY position. So they don't know what it means to stay put.
Okay. Yeah.
You see what I mean?
That makes sense.
Yeah. Yeah. If you don't do that, then yeah, then they can cheat. And even when you do that, they can cheat. So you have to wiggle it around and do all the other stuff to prevent it from cheating. But yeah, we do all of that. Yeah.
Okay, that's great. I'm not sure if there are more questions. If I may ask another one. So the representation that you learned, right, with self-supervised learning, the representation are kind of very specific. Do you have a feeling that the representations learned this way are more suitable for a particular task than the other ones?
Oh yeah, definitely. I mean, well, I can tell you what they're not suitable for. They're not suitable for, object category recognition, right? Because you see only the same instance, because it's based on tracking, right? So you're basically all the time, what you're learning is you're learning variations of the same instance, maybe due to lighting, due to viewpoint, scale, occlusion, all this stuff, but you never suddenly see like a different mug, right, appear in the place of the original mug, right? So you are not going to be invariant to differences in, within class variation. So that's why it's not going to work well at all for something like Pascal or ImageNet. Okay. Now my hope is that it will work well on something like tracking, but I'm kind of hoping that you guys can tell me if that's true or not. But the hope is to actually learn a feature that is kind of instance specific, that it's kind of keeps the instance identity, but then kind of averages away everything else about it. The lighting, the viewpoint, blah, blah, blah.
Right.
Yeah, but basically semantics, it's not going to learn. By design, yeah. And frankly, like if you were to use it, you know, in a kind of an overall system, one way you can do it is you can maybe take this feature, concatenate it with something that's learned from semantics, and then together you'll have kind of both. You'll have kind of
like some kind of a colorization. Some kind of a colorization self, you know, other types of
colorization one, yeah, and that will kind of get you, you know, the benefits of both, hopefully. But again, this is not, we haven't really looked at that, but I would love to know. And so if you guys try this, and if it works or it doesn't work, please email us either way, and we will love to hear.
Very good. Any other questions from the audience? I think there were a couple in chat.
I think we already picked up every question from the chat.
Hi, I have a short question. Hi. So it was actually a great talk, and it's interesting to see such self-supervised work from your group. Do you think that there's a way to combine the self-supervised features with active supervised learning in order to achieve, say, improved performance on a specific target set?
You mean active like on online, or what do you mean active?
With available supervision.
Oh, I see, like semi-supervised. Yeah. So that's, yeah. I mean, that's basically what semi-supervised learning is supposed to be, right? So you have a little bit of data with labels, and then a whole bunch of data without labels. Yeah. I haven't seen it. Like, everybody wants this. This is definitely, obviously, the right thing to try to do. I haven't seen much that is that cool yet. I think there is some new stuff that might be coming up soon, but it's obviously the right direction, right? That's what we all want to do. We want to have a little bit of supervision and then kind of use the rest of the data kind of to get, yeah. Yeah, so that's obviously the right direction. I'm not sure I can report any great breakthroughs yet. At least I haven't seen anything. There's always, you know, people report, you know, a couple of % better, you know, but yeah, everything could be made a couple of % better. So like, I feel like it should be like, you know, twice better. So I haven't seen anything like that, but I think that's a great direction to work on, because that's just gotta work, right? It makes sense for it to work. Yeah.
Yeah, exactly. So when the cycle consistency paper was out, I had the feeling that this can be essentially used as at least as a pre-training set for tasks such as Davis, where you don't have much annotated data.
Right.
But I did not see any work, and then honestly, I didn't try myself yet in this direction. So.
Yeah, I don't know. I mean, we tried a couple of times in various scenarios, and we were also like, you know, 1% better, you know, nothing that exciting. So yeah, I guess we're missing something here. It's yeah, I don't know. But it's a great problem to work on. Yeah, it's just hard.
Yeah. Thanks a lot.
Mm-hmm.
Yes, so I think that there don't seem to be more questions at this point. So thank you very much again, Alyosha.
Oh, it was a pleasure, and it's wonderful to see you. I hope that it's not too late in where you are.
I've gotten used to it over this week.
Oh, okay. Okay. Well, yeah. I thank you for inviting me, and lovely to chat with you guys. And yeah, thank you. And next year, hopefully, real life.
Yes. Yes,
all right.
That's the big hope. Yeah.
All right. Stay healthy,
okay,
everyone.
Great.
Thanks a lot.
Thanks, you too.
Attending.
Bye.
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 So yeah, that brings us to the wrap up. So thanks everybody in the audience for staying that long. I think it was a great workshop overall. We had lots of interesting talks, lots of interesting results, and there are a couple more organizational things to announce from Paul. It's a general opportunity for wrap up. So if you have any remaining questions, please feel free to ask.
Okay. So yes, the organizational things Bastian meant. So first of all, we should acknowledge the sponsorship by Google, who sponsored some money. And what we also didn't say so far yet, we use this money we got from Google as a prize money for the competitions. So unfortunately, this has to be splitted among the 3 tracks. So in total, we have $500, which will then be divided by 3. So please contact us to claim this.
Also, you will get a certificate. So this will be sent to you by email. A nice certificate with your names, paper titles, and stating the rank in the competition. So that's usually quite useful to prove that yes, you have really achieved first rank here.
Exactly. Yeah, and then we will try to make the slides of the speakers, or at least the ones who are willing to share them, available in the next days or week. And we will also upload the papers which were submitted for the competition soon. And yeah, I'd like to thank again everyone who participated for all the efforts, and I hope that maybe we'll have at some point another edition of this workshop or challenge, and hope to see you all again. Okay, so if there are no questions or comments, I think this will be the end of the workshop. There were only 6 participants now in the Zoom session, and there's still 21 people watching the live stream.
Yeah, it's been a long day and quite late already in quite a number of time zones. So yeah, thank you everybody again for participating. It was your active collaboration, your active participation in the workshop that really made it a great experience. And also thanks to organizing all of this. So this was also yeah, great work on your side. So thank you.
Yeah, thanks as well for organizing, Bastian. Yeah. Okay, so I will stop the YouTube live stream now.
Okay, bye everybody.
Bye everyone.